Okay, so good morning, everyone. Welcome back to the PtRC Project Outreach Training Program. This is the second day uh, of this last, as we said, the last campaign of this edition of the Outreach Program. Okay, and I'm sure you enjoyed yesterday's sessions dealing with both the Newton physics as well as the INO project per se, and also the last session where a number of environmental concerns and other myths and misconceptions were dealt with. And it was very nice because you had very actively interacted with the speakers, and that is what is the main aim of this program. It should not be just one way of talking. And today we have again Professor Vigyan Prasar, the former project director of the INO project, which is now PtRC project. She is now going to take you through actual various experimental activities that are happening, that are built, that are collecting data, that are actually showing that the instruments and the developments that we actually achieved are in tune with what are required for the final ICAL detector and so on. So in the process, of course, he's also going to describe the workings of these detectors and why a particular detector choice and so on and so forth. So today's talk is more on, the first talk is more on the ICAL experimental activities that the collaboration has undertaken for last about 15-20 years. But I also want to specially announce the second talk, which is, again, as we said, about the spin-offs and the benefits of INO for local communities, is going to be given by a person who is more close to your age. And I'm quite sure that he will strike a good chord with you, and that will be a good resonance in terms of views as well as the person speaking. Otherwise, you have been hearing about very senior, very distinguished, but very senior people, scientists, but I think you will enjoy the second talk equally well when one of our graduate students, Mr. Jones Panicker, is going to come and talk about the spin-offs of this project. And you can interact with him, not just what he speaks, but also, like what kind of lifestyle, how he enjoys the graduate studies in INO, etc. So this is like a one-on-one nice interaction that you could have. And as we promised, the last one, of course, is going to be on more personality development, the skill development, personality development of how you improve your public interaction and communication skills. And the last session today at 3:15 is the one where you must keep all your questions of all types, and then where all the faculties that you saw yesterday and today are going to be available. So it's a very, as we said, it's like a freewheeling kind of discussion and queries. You can ask every question under the sun on whatever you have, whether science or career development or INO or why this, why late, why there. I mean, every single question. Okay, so without actually once again taking more of the faculty's time, so let us invite right away Professor Vigyan Prasar, who is currently the Raja Ramanna Fellow at the Institute of Mathematical Sciences, Chennai. He's going to talk now at, the talk is titled as Science at IHF and PtRC. Over to Professor Datar.
Okay, thank you, Satyanarayana. Good morning to all students, my friends. This is the title, but of course there will be lots of overlap with the talks that you might have already heard. But my excuse is that just like a Hindustan or whatever classical music is played based on ragas, raga, sung or performed by one artist is the same as the raga performed by other artists, but the way the performance is made is different. So that's my excuse for some of the things which you already know being said in the slides. My email address is given here, so you're welcome to write to me if you have any doubts on INO or neutrino related any physics questions as well. Okay, so let me start. This is the plan of my talk. the what and why of the iron calorimeter detector at the Pottipuram Research Center, earlier known as the INO. Then I come to the mini iCal detector at the Madurai Transit Campus, and the upcoming engineering prototype iCal detector that is in the ICHEP campus. Okay, so what science can the iron calorimeter do? The iron calorimeter is the only magnetized neutrino detector, okay, to study atmospheric neutrinos and antineutrinos, and they can be distinguished from each other, as we will see, and over a fairly large range of energy, so 1 to 20 GeV, and over a large range of distances, about 10 to 13,000 kilometers. 13,000 kilometers, of course, the diameter of the Earth. So you can get neutrinos from the top of the atmosphere reaching the detector, but you can also get neutrinos from the other end of the Earth because the atmosphere surrounds the Earth completely, and that's how you can get these distance scales. One of the nice things that we can do with this iron calorimetric detector is the so-called mass hierarchy or the mass ordering of the three neutrino mass states. We've already seen in these earlier talks that there are three kinds of neutrinos or three flavors of neutrinos, but there is also another basis which is different from this so-called flavor basis, which is the mass basis. And then there are three masses, M1, M2, M3. And so we know the ordering between M1 and M2. M2 is higher than M1. We know from solar neutrino experiments, but we do not know whether M3 is larger or smaller than M1. Okay, and that difference is also large. M3, M1, M2 difference is quite large. The delta M squared, so, which you must have seen in the earlier talks. Okay, who are the competitors for to us? Well, there is Juno, which is also going to look at the mass ordering problem using reactor antineutrinos. They are building a 20,000 ton liquid scintillator detector, which is doped with gadolinium, and 50 kilometers away from the reactor complex in China. They are going to, they've already commenced construction, and they will probably start data taking by 2022 or maybe 2022 end. Then there is Dune, which should start and perhaps get early results in 2029, 2030. That is an accelerator-based experiment. So neutrinos produced at the accelerator site, Fermilab accelerator site near Chicago, they will travel 1,300 kilometers through the Earth to a detector in South Dakota, where Davis did his pioneering solar neutrino experiments. Of course, this is a different cavern, a much bigger cavern as well. And there will be liquid argon detectors. The design or the goal is to have three such detectors, 3 or 4 such detectors. But they might start out with 2 of about 15 to 17 kiloton each. Now, the iCal so-called 3 sigma result in a standalone basis will be about 10 years after it starts taking data. But we already know that there are other experiments. So if you use that data as well, then you can get the mass hierarchy in a shorter time, about 6 years. Now, even if these other experiments have gotten their results, an important result like the mass hierarchy needs confirmation by other experiments. Because it has happened historically, we know of cases where results have been different from the results that were, 2 results can be different and they may not agree with one another. Then a third is required to perhaps settle the issue. So there being more experiments than 1 or 2 is not a problem. It's actually good for the science. Okay, what else will iCal do? It will discriminate between vacuum and matter-modified neutrino oscillations. Again, you must have heard yesterday that there are these so-called vacuum oscillations. That means as neutrinos propagate in vacuum, the mass eigenstates propagate differently. Okay, because if you have the same energy and but a different mass, the speed of the neutrinos is different, and the speed affects the phase at which the wave, the equivalent particle wave propagates. And so therefore you have a different mix of these mass eigenstates, which when projected onto the flavor eigenstates will show a mix of let's say nu e, nu mu, and nu tau, where originally you might have started with, let's say, nu mu. Okay, and then it's also true that matter modifies these oscillations because it changes the mixing angle. So you get you have the vacuum mixing angles and the vacuum delta m squareds. When neutrinos propagate in matter, because of the interaction with the electrons in matter, the nu e is affected, and then that in turn affects all other neutrino flavors as well indirectly. Okay? So matter modifies these neutrino oscillations. Now, for this modification to be significant enough to be detectable, the neutrino has to travel reasonably large lengths in matter. That is possible with dune. For instance, such effects will be completely negligible in the case of the Juno experiment, where the distance is only 50 kilometers. In dune, it is about 1,300 kilometers. So it is becoming important. Whereas in ICAL, we can go up much larger lengths, so where matter effects are certainly important. Then these matter-modified neutrino oscillations, actually the heart of that is the so-called MSW effect, the Mikhail-Smirnov-Wolfenstein effect. So this in this formulation, you actually see that some of these parameters can be resonantly enhanced, and so this resonant enhancement can only happen when you have large matter lengths with the neutrino propagate, and therefore this is observable by ICAL. And in fact, this could be the only experiment that can observe the MSW resonance, because at certain energies you will get this resonance. Okay, then there is synergy with accelerator experiments. That means we are complementary to accelerator experiments, especially in the area of particle-antiparticle symmetry violation. This has to do with the fact that the universe that we see around us is all matter, and there is very little, if at all, any antimatter. I mean, of course, antimatter is produced in interactions, but on the whole, it's a matter-dominated universe. That means you don't have let's say, an anti-Vivek Datar that could be possible somewhere far away in the universe. All of the universe, as far as we know, is matter. Okay, there is almost no antimatter. Okay, now given that, then one has to understand it. And this could arise in some theories due to so-called CP violation. That means there is, to start with, in the Big Bang, you made an equal number of particles and antiparticles, but because of this interaction, which violates particle-antiparticle symmetry, there is a slightly larger number of particles as compared to antiparticles. And then when they annihilated and produced radiation, that small difference showed up, and that is what is surviving to this day. That is, we have a particle-dominated universe. Okay, so this is a very important question, probably one of the 10 important questions in science, leave alone physics. Okay, then there is the possibility of doing tomography of the Earth using these very same matter effects. Now, of course, you know that X-rays tell us about the interiors of objects, including, for instance, human bodies. They have been widely used by the medical profession. But can we X-ray the Earth? Neutrinos offer that possibility, because neutrinos can indeed traverse the Earth almost without any attenuation, and there is no other radiation that can do that. Okay, so I mean, all other charged particles and neutral particles have interactions which are much stronger, and they would all get attenuated, so you can't really probe the interior of the Earth, but neutrinos offer that possibility. And this kind of tomography would be complementary to the seismic information that we have. We already have a lot of that information. So these are two very different techniques, but trying to get at the interior of the Earth. Then there is the so-called beyond standard model physics. the fact that neutrinos have these masses are very tiny, very different, of course, from zero, but also very different from the masses of the lightest lepton, which is the electron, indicates that certainly the standard model is not the ultimate model of for high energy physics. So people have been looking for beyond standard model physics, anomalies or things that cannot be explained within the standard model. Standard model, by the way, has been extremely successful in almost all the data, except for a few things, like, for instance, neutrinos, or, for instance, the existence of dark matter, and so on. So, for instance, the ICAL detector could probe these so-called beyond standard model physics, including non-standard interactions. So, hypothetical as of now, but who knows? We might one day find evidence for them. Then the so-called sterile neutrino, magnetic monopoles, which is something that Dirac had worked on. Also, our own Saha, Meghnad Saha, and things like dark matter decay or annihilation in close by stellar objects, such as, for instance, the sun. And if you want to find more details of this, please look up this white paper on the physics with the iron calorimetric detector in Pramana, which is a journal published by the Indian Academy of Sciences. And I think you can freely download these articles, if I'm not mistaken. In any case, this should also probably be there on the INO website at the IFR. So this is the reference. Okay, now, so I have already told you about the first bulleted point. What is it that iron calorimeter does? It measures atmospheric neutrinos in this energy range 1 to 20 GeV. Of course, it can also measure higher energy neutrinos through their interactions, but it can't tell you very much about the energies of these higher energy neutrinos because the bending of these higher energy muons will not be sufficient to be able to quantify. And of course, as I said already, that you have propagation lengths which it will probe, which are very large, which have a large range, all the way from 10 to 30,000 kilometers. And of course, it is needless to say that they come for free, that they're always present. They're naturally present. Okay, then the atmospheric neutrino experiments hitherto, such as the biggest detector for that is the Super Kamiokande detector. When the Hyper Kamiokande gets built, which is 10 times roughly the Super Kamiokande, that will also measure atmospheric neutrinos. But they will not be able to distinguish clearly between neutrinos and antineutrinos. Certainly not on an event-by-event basis. There are other possibilities where they might get some information, but those are for, I'll not touch upon that right now. Remember, this is for atmospheric neutrino experiments. Of course, accelerators which produce neutrinos and antineutrinos in separate runs, you know that the beam that you started with was a neutrino, or the beam that you started with was an antineutrino, with possible contaminations of the other particles. That means if you have a neutrino beam, you will have maybe of the order of percent level contamination of antineutrinos and vice versa. But at least you know the predominant, but that is for accelerated neutrinos. Atmospheric neutrinos, this will be the only experiment to distinguish. And how is that done? For instance, the nu mu interacts, let's say, with a neutron in the target. In our case, it is going to be iron, to produce a mu minus plus a proton. And then you will track this mu minus because it's a heavy electron and it travels through the detector more or less. The analogy would be like a bull in a china shop. Okay? It would just keep on going. It would get force, it would lose energy in the iron, and it would also get bent due to the magnetic field. But it behaves quite differently from an electron, which in fact the electron or the positron produce an electromagnetic shower. You don't get long tracks from electrons or positrons, whereas the muon, it mainly, at least at these energies, loses energy through ionization, and therefore there's no question of pair production of these energies, and therefore it just keeps on moving till its energy becomes zero. Okay? Okay, the anti-muon neutrino interacts with the proton to produce a mu plus a neutron. Okay. So the mu minus and the mu plus can be distinguished because of the magnet, and that is what is there in the next slide. So why make this huge magnet? Okay, there are two reasons, of course. One is that you want to distinguish between muon neutrino induced events and anti-muon neutrino induced events, because they will produce either a mu plus or a mu minus, and when they see a magnetic field, they will bend in that magnetic field. So if you know the direction of movement of these muons, you can tell which direction, of course, it came from, but also you can tell whether it is a mu plus or a mu minus. Okay, but there is another purpose to this magnet, and that is that iron is one of the cheapest substances with which you can make an electromagnet, and it also is fairly dense. It has a density of about 8 grams per cc, and it is fairly cheap. So you can make a magnet, and at the same time you can use the iron that is there in the magnet to be a target for the neutrinos or anti-neutrinos, as the case may be. Okay, and then they, as I said already, they produce muons which are charged, and then they can be trapped, and therefore you can go work back and say whether it was a mu that interacted or an anti-mu. Okay, then this is just another box which says why go underground? Okay, because cosmic muons are the most important background, and how deep you have to go, about a kilometer, which makes roughly a million-fold reduction, maybe slightly less than that. But to get this kind of reduction in the cosmic muon background, which because, by the way, just for just as a quick order of magnitude number to remember, about 200 muons, cosmic muons, cross a 1 square meter cross section every second on the surface of the Earth. Okay. Now, of course, it depends slightly on the latitude. So at equatorial latitude, it's slightly less. At the North Pole, it would be more. But this is just a rough number which you might like to remember. 200 muons per square meter per second. And that gets reduced by between a factor of 10 to the 5 to 10 to the 6 when you go 1 kilometer deep. Okay, now, if you want that kind of cover, rock cover, then of course you can go to the sea or to a big lake, but that makes it logistically difficult, because then there is pressure. Every 10 meters, there is a pressure increase, as I said yesterday, and therefore it is better to go into a mine or a tunnel. Now, mines have a problem in logistics, because you can't drive trucks into mines unless they are of the type where you already have access that way. It is so in the Kamioka mines, but and maybe one or two other mines. But generally speaking, mines have vertical shafts, so you can't take a truck there, and they have limited volumes. So typically 2.5 meter, 3 meter by 3 meter or so, and therefore you can't take big plates, for instance. You can't take big pieces of apparatus. Whereas if you have a tunnel, then of course we know that tunnels have been used for long for traffic. Road traffic, or you can have trains moving and so on. So tunnels are a much better way of getting to the logistics of such a detector, of making a cavern for such. So tunnel is certainly the choice, and the pioneer in this case was probably the Gran Sasso laboratory, which tagged on to a pair of tunnels through the Gran Sasso mountains and made a side cavern somewhere along this highway, string highway, in the tunnel in Gran Sasso mountain. Okay, now how much does this muon flux come down? What is the behavior of muon flux as a function of depth? This is the behavior, and Pottipuram is somewhere here in this red line, of the order of about something like 5,000-6,000 muons per square meter per steradian per year. Okay? KGF was the deepest, and that had hardly about 30 or 40 muons per square steradian per year per square meter. snow is shown here. For instance, we did the solar neutrino experiment, Bransas was here. Push-up, had we got that site, would have been somewhere here in the Singada, near the Singada underground power station. And this is Pottipuram. Kamyok, as you can see, has a smaller cover. It has a larger background. Okay. Now, let me go to the next slide. Okay. This is the plan of the access tunnel and the caverns. So we make a tunnel which is about 2 kilometers long, and that's not shown here, that you might have seen in the slides yesterday, shown by Indumati. And then you come into a complex of caverns. The biggest cavern is this cavern 1, which will house the ICAL detector. This cavern is of the order of 130 meter long and about 30 meter wide and about similar dimension in height. Then there are smaller caverns for other experiments, and also for the control room. The control room will be housed in one of these caverns for the ICAL experiment. But these caverns can house experiments such as the neutrino-less double-beta decay experiment or dark matter experiment and so on. So this 2 kilometer long tunnel has a D shape. The cross section is shown here. Okay? So the top of it, the curved part of it will could carry, for instance, services like water, like electricity, like maybe some gas lines and so on. And this would be about 7.5 meter wide and similar dimension for the height. If there is a need for a safety tunnel, for instance, it could come below this with some thickness of rock in between. Now, there is also, we think that we will gain a little bit by having a downslope from the entry to this tunnel, so-called portal, and have a downslope of about 1 in 13.5 or so, where because of this length of the tunnel, you will gain about, let's say, 150 meters or so in depth. So you will have that much additional rock cover at the site, at the cavern site, and that many fewer neurons. You can't go much more than this. For instance, if you can you go to 1 in 7? No, that would be very sharp, slope. On the other hand, if you go to 1 in 20, then you don't gain that much. You gain much less. Okay? So this was a sort of optimal thing that we thought about. Basically the engineers, civil engineers thought of this. Okay, then this is the vertical rock cover, but there is, at all places it is not this, obviously. On the sides it is less, but there is still a 1 kilometer rock cover on all sides. It would make of the order of 3 years to make this tunnel and the caverns. This is the cross-sectional view of the cavern where the ICAL detector is housed. You can see this very tiny figure here. I don't know whether you can see this, my pointer, but on the right-hand side, the lower side, there is a cross-section of the ICAL cavern. And on the left-hand side, you will see a small figure. That's a human being shown in comparison to this very tall structure. The ICAL detector, incidentally, is about 50 meter long, about 16 meter wide, and about 15 meter tall. Okay? And sits, of course, on some support structure. That's the size of about the Olympic size swimming pool. By the way, I should just check with Satya and with the students that are you seeing the change of slides, please?
Yes, we are seeing her right now.
Okay.
We are at,
okay.
Yeah.
Now this is the next slide, which shows a schematic of the iron calorimetric detector. If you don't see that, you please let me know. One of you can unmute and then just tell me that you're not seeing the next slide. Okay.
Sure.
So this is the schematic of the iron calorimetric detector. This is really a schematic because it doesn't even show the coils. So the coils are shown in this schematic, slightly better. So there are these 4 sets of coils which produce the magnetic field, and that the top view of this is shown along with the simulation results. These simulation results are from a so-called finite element simulation code, electromagnetic code, and let's say the current moves in a clockwise fashion. So here on top, it moves from left to right, and on the lower side, which you don't see, it is going the other way around, and that's how the current is flowing in this coil. Okay, and you can see that the magnetic field is maximum here, and then turns around and comes back through the iron back into the central region. So it comes around on both sides. So you can see there are regions where the magnetic field is low, such as these blue regions, but about 90% of the magnet has about greater than 1 Tesla field at 60 kiloampere turns. This is where the simulation is done. The steel that is used here is so-called low carbon steel, which has a good BH hysteresis curve. In other words, when you reverse the current, then you can get back a magnetic field which is in the opposite direction. But when you, let's say, zero the current, then the field is fairly low, the order of half or something. It's not like in a permanent magnet where it remains at a very high level. Okay. So this has these properties, and also it has good magnetic properties. In other words, you can magnetize it to about 1.5 Tesla on such a macroscopic scale. And in between layers of this iron, there is a gap of about 4 centimeters that you can see here in the cross section. 5.6 centimeter is the thickness of the iron plate, roughly about 4 meter by 2 meter, and that is tiled to sort of complete this surface of 16 meter by 16 meter for one layer of one module. Okay? And then there are about 150 such layers of iron. But between that, there are spaces to keep a certain gap of 4 centimeters in which you slip these glass RPCs, which are roughly of the order of 2 meter by 2 meter, and which have X and Y pickup planes, signal pickup planes, and 2 millimeter gas gap to apply high voltage. I think that will probably be discussed by Satyanarayana, or maybe he has already discussed it. I forget now. But you apply a high voltage of the order of 10 kilovolt between anode and cathode on the coatings outside of the glass on either side. And then there's an insulator, and then there are these pickup panels. So from the same detector, you get a signal that a muon has traversed, or indeed any charged particle has traversed this detector, and you will get a position which is picked up by these X and Y strips. Okay, the strip width is about 3 centimeter, both in the X and Y planes. So that is the kind of, decides what is the resolution that you can get in terms of position. But in the same detector, you get both X and Y. That's the idea. And then, of course, depending on which layer this is, you get the Z. So you can track this muon through these detectors. Okay? And you can look at the curvature, you can look at its stopping, how many layers it traversed, and so on. Because the neutrino can interact anywhere in this, right? It can interact somewhere here, but it can also interact at the center somewhere or at the other end if it is coming down, and vice versa if it is going up. Okay. It can, in fact, even traverse these detector modules. It can come, it can start at module number 1, but it can go on in module 2 and module 3. That's also possible. Okay, so I go to the next slide, which is gives you some features of this 17 kiloton ICAL magnet module. There are, as I said, there are 3 such modules which make up about 51 kiloton of the ICAL detector. The magnetic field, as I said, is greater than 1 Tesla at the currents that I talked about, the ampere turns that I talked about, more than about 60 kiloampere turns. Over 90% or so of the volume of the detector, volume of the iron in the detector. Of course, the field in the gaps is very small. And you can, in principle, go up to 1.5 Tesla in the iron itself at the center, for instance. So the design goal was we will see how it is met. It is met in the case of the mini-ICAL detector emissions. Okay. This magnet, by the way, is very different from the normal gap magnets that we have, where you have a field between the pole pieces. So you must have seen a C kind of magnet, which is there in labs, or maybe also if you put 2 C's together, you can have still a gap at the pole pieces at the center and a gap, and that's where you get the magnetic field. But this magnet is very different because you induce a magnetic field through the coil, the current in the coil, but then the field closes on itself. Okay. Ideally, you would have had no air gaps, but then, of course, it would become unmanageable. The plates would become so heavy that you won't be able to place them, and also it would be difficult to manufacture and carry these plates. So these are tiled, but the gaps are kept to a minimal level. So the field actually travels through the iron most of the time, except, as I said, for these gaps where there might be a small fringe field. So this is very different from the normal gap magnets or indeed solenoidal magnets. Now, the field, the fringe field, that means you go away from this magnet, let's say about half a meter away, then this field reduces to less than about 10 to the minus 3 Tesla. So here it is a Tesla, and it reduces to less than 1,000th of that value as soon as you go. In fact, this number is, in the case, we have measured it in some other magnets with larger gaps. In fact, this number is even like 0.2 meters. This module and 3 of these modules together will make the largest iron-based electromagnet in the world. There are solenoidal magnets, for instance, superconducting solenoidal magnets, such as as that in the Atlas detector for experiments at the LHC. Those are probably somewhat comparable or even slightly larger in size. But iron-based electromagnet, this would be the largest in the world. This I have already said, 150 layers of soft iron low carbon steel of dimension 16 meter by 16 meter, tiled with 4 meter by 2 meter by 56 mm thick plates. And there are several manufacturers in India who can do that. The gap between the successive layers, our design goal is 40 mm. We will see how we do with the engineering ICAL module. If there is some difficulty, we might have to increase this gap a little bit and then add a few more layers or decide what is the best course of action. For the glass resistive chamber, it means that it can at most be 35 mm thick, perhaps even smaller than that, 32 mm or so. Design code. What are the challenges and issues? Of course, one is of the large size. We have never made in India such a magnet. Indeed, nobody has of this size in the world. It has large copper coils. So they are about 8 meter wide, 15 meter tall, and they have to carry up to about 80 kiloampere tons. And the coils itself would weigh something like 150 tons. And these have to be made from so-called oxygen-free high conductivity copper. Now, it would have the largest mass, as I said. The assembly of this magnet is another slightly intricate thing. You have to minimize gaps. You have to make sure that over this whole area of 16 meter by 16 meter, there is reasonable planarity, because otherwise you will start getting misalignments, and the RPCs will not go through the whole length of this, the gap in this so-called of the road, the gap between the subsequent iron planes. There has to be piecewise uniformity of the B field, and this should lead to about a magnitude of the magnetic field 1 Tesla over 90% of the area. We need to measure the interior B field actually, although we don't have right now the best way of doing that. We have a possibility, and we are going to work on that possibility using stop cosmic mu pluses in the detector. But that's that's only a possibility. Until we have shown whether it works or not, we will not know. But the other methods are more indirect methods, using Hall probes in intentional gaps, or using coils which surround these plates, which are wound around the plates. And so when you ramp up the field, you get an induced EMF, the Faraday, remember the Faraday effect, Faraday induction, and also when you ramp down. Okay, so this certainly will be used, but they give you an average magnetic field over the cross-sectional area of the plate. And you can do that only at a finite number of places. So if this other method works out, then at least for the engineering ICAL, we will be able to say that do we agree with the other methods or not. Of course, if that method is not feasible, then the only thing we have to rely on is these pickup coils and Hall probes. The other is the stability of this magnetic field. One is the mechanical stability. Of course, we know that when you switch on the current, the plates tend to come together because of the attraction due to the magnetic field. And whether that will remain stable with time and also with whether the B field will be stable to 1%, it seems to us that this is not such a challenging thing. But certainly the mechanical stability over long periods of time, we will have to see, gain some experience. The other big challenge is, of course, the large number of resistive plate chambers, the detectors, gas detectors between layers of iron to pick up the muon signals. They number 30,000, which is of the order of 3 times or so the total number of RPCs in the whole world at the present time. The electronics is also challenging for a project in India. We have never built so much of electronics. But if you compare it to, let's say, experiments in LHC, then this is much smaller. They have hundreds of millions of channels. So the 4 million channels is not so large as compared to some of the big experiments. But certainly, we have not built anything in India which is so large. The other challenge is that the electronics should be fast, which is nanosecond time response, and also the power per channel should be per channel. I mean, each of these RPCs has 128 strips readout, and that's how you get these 4 million channels. And then each of these channels should consume a power of less than 50 milliwatts. Okay, so if you want to gain experience before you actually build the detector, and this is absolutely a must, otherwise you might come in for big surprises and perhaps even disasters. So you want to build something on a smaller scale, get some experience, make mistakes, learn from those mistakes, correct them. And so the first step that we took is to build the so-called mini ICAL detector at the rented INO Transit campus in Madurai. This is about 85 tons. So that's about 1 by 200 of the size of one ICAL module of 17 kilograms. Okay? And this is the largest magnet or the detector that we could fit into the hall that we had in the rented campus. And so this is about 4 meter by 4 meter and a height of about 1.3 meters, including coil. Okay? So this is a picture of that detector. It has been working now since 2018. And these are some sample tracks which show curvature of the muon in the bending plane and is more or less straight in the non-bending plane. Of course, it may not be perfectly straight because of so-called straggling. The muon can scatter off a nucleus and change its angle. And perhaps this is happening somewhere here in this track. But we have many. This is just one. This is a sample track. There are many such tracks, and we observe both the curvatures, this curvature as well as the opposite curvature corresponding to mu plus and mu minus. And these are pictures of students assembling RPCs before they are slipped into this gap here. And perhaps some of you have already been to ICHEP. Okay, so this is another picture of the 85-ton mini ICAL detector at the INO Transit campus. Again, some pictures here which show some of the group members who have been responsible for assembling this ICAL magnet, mini ICAL magnet. These are some of the components as they were being manufactured or being machined or being put together. So, for instance, the iron plates as they came in from the mills, steel mills, in this case it was SR from Gujarat. Then these plates were taken to a workshop in Bihar or Jharkhand, and they were machined to the right size. And there were various sizes that we needed for mini ICAL. The largest one being about 2 meter by 2 meter, but then there were smaller ones about 1 meter by 2 meter and so on. So there were, I think, some 5 or 7 different sizes of plates, and then they had to be multiplied by about 11 because we have 11 layers of iron in the mini ICAL magnet. These are the spacers and pins which keep the gap between the successive layers of iron. This is a copper conductor spool. This is actually oxygen-free high conductivity copper. This had to be imported because there is no supplier in the country. But hello, can you see this slide, please?
Yeah.
Yeah. Okay. So this had to be actually unwound, and it turned out that about 85, I think 80% of the time went in actually untwisting this copper conductor. And this copper conductor, by the way, is quite large in cross section, about 35 mm by 35 mm square cross section, and has a hole in it of about 17 mm inside, 17 or 19, I forget, but it's of that order, to carry low conductivity water through it to cool the coil which is carrying a large current. Okay? So the I squared R loss in the copper conductor that is taken away, that heat is taken away by a water cooling system. So this is the conductor bending machine, because after all, this is to be bent. So the conductor was made in the form of U and C. Okay, and so the U was the bigger one with the larger length arms, and that was put in first, as I will show you in the next slides. And these U's and C's were actually made from this coil in the central workshops in the Baba Atomic Research Center. They did a beautiful job of this, and they also developed the method of actually brazing, silver brazing this C and U. So they tried this out and tested it for pressure leaks or for resistivity and so on, good conductivity, and they perfected this method using a induction brazing machine at Bombay and at Mumbai, and then they sent two of their experts to Madurai to carry out the task in situ. So the next slide actually should show the assembly of this mini ICAL detector. So you first have to make these pillars on which the whole magnet will be supported. They have to be reasonably plain, and then these are some insulating material, G10 boards. So because the copper conductor is carrying a current, so it should not should not leak out even a small amount, and that's why this insulator is put below. And then these are the U's and C's. So you see the U's installed in place first, even before the plates are put in, and then the plates one by one are put in, and so you make this assembly around the copper without damaging the copper, because copper, by the way, is much softer than iron, and these plates are also very heavy. So this was actually quite a skilled job, which a group of people did. They're really experts in such assemblies. So they did not even hurt any of these any of the coil sections. And after that was all complete, then the C section was put on top one by one. They were braced, and there were, I think, 36 plus 36. So 72 of these, or was it 18 plus 18? I think it was 18 plus 18. Okay, so 72 bracings were done, I think, and also some few others. But all these were done by these experts who came in from Mumbai, and they were done really to perfection, because they did not show any leak. They have been working since that time now for the last maybe 2 to 3 years, and they also had good conductivity. I mean, electrical conductivity. Okay. This is the low conductivity water cooling system. This was designed by the BRC group and made in industry, I think, in Bangalore. And this cools water, chills it, but also it's the water that is used is low conductivity distilled water, so that doesn't do any harm to the insides of the OFHC copper, and at the same time cools. Of course, this water is also used for cooling the power supply that actually powers this coil. So the power supply is to the left of this. To the right of that is the hall where the magnet is situated. Okay, this is the mini ICAL in terms of simulated field, three-dimensional simulation program package was used, and this is the place where you place these Hall probes to measure the field in the gaps. As you know, the Hall probe, I hope you know the principle on which the Hall probe works. That is, when you have a current flowing in a semiconductor, if you apply a magnetic field transverse to the flow of that current, then you get an EMF in the third perpendicular direction. And you can measure this field. And depending on the material, the field and the current that you send through the semiconductor are related to the so-called Hall coefficient. Okay? And so by calibrating this in a known magnetic field, you can actually get a measure of the field. And so we had several positions in which this Hall probe was placed. Again, this Hall probe and the measurement system was designed in India by a company in Pune. And these are some other pictures of the Hall probe PCB in the gap. So you have to insert it in some locations, such as this, and in a few layers only. There is a possibility of putting this in layers 1, 6, and 11. Okay? And this is a picture of the Hall probe strip. So there are several Hall probes in this. And this is the power supply that powers this electromagnet. It sends current up to 1200 amperes. Actually, it's not 1200 because, of course, some voltage drops across the conductor that carries this current to the magnet coils. So it turns out that you can go up to safely about 900 amperes or so. And then you also have these surge coils. So these are just indicative of where these surge coils are. These plastic tags, they indicate where this coil is around the cross section of the plate. So these surge coils are, of course, then coupled to some electronics, and they tell you how much is the change in magnetic field and the related EMF. And so you can calibrate that again. Okay, so you can get a measure of that. Then these are some of the other things, just some pictures which show you, how the glass RPC gaps were made at Saint-Gobain. Of course, once the gaps were delivered and the leak checked and so on, and also surface resistivity maps were made at the factory, then they came to Madurai, then they were again checked and also assembled for making the full detector together with the electronics and the gas in and out supply tubes. Then there is this closed loop gas system, again, which was designed in India. This was in collaboration with TIFR and a company that makes this. But then later on, we also had some collaboration from the Atomic Research Center engineers. Then these are some of the ICs that were used at various stages of developments with RPCs and the electronics, associated electronics. This is something that was an important role was played by the electronics division of the PtRC. Then this is the DAQ card. This was mainly designed. This was the work of the TIFR group, which made this in a very compact way. And so this sits in one corner of the RPC module. It's a two-layered, two-floored structure of electronics. This is the high voltage, DC to DC high voltage card, which takes low voltage at typically 5 or 12 volts and then converts it to plus or minus 5 kV, which is applied to the anode and the cathode. They showed you in the diagram. And so it generates about a 10 kilovolt across the detector. So you only have to send in 2 thin cables, which give you low voltage to this board. And this sits at the opposite corner from the DAQ card. This is the front end electronics board. This sits on one side of the RPC. So this is, let's say, for the X strips, and then for the Y strips, you have it on the other side at right angles to this. So this is the kind of dead area of the RPC module. But this is something that is absolutely necessary if you want to process the low signals which come out from the RPC. The signals that come out from the RPC are of the order of a few millivolts, and these are again of the order of 80 to 100. And so then you can process them. You can have discriminators and so on that operate at, let's say, 20 millivolt threshold and whatnot, and then give you logic signals that are then processed for making coincidences and this and that. There is also a trigger and calibration system. You want to know the health of this system and also to generate the triggers. So this is a fairly complex system by itself. And again, this is a TIFR BRC collaborative effort. So with all of this, once the detector starts working with the magnetic field, with the current flowing through the copper coils, then you can measure cosmic ray muons in miniature, because after all, it is on the surface. You have lots of cosmic ray muons, as I said, of the order of 200 per square meter per second. And therefore, for an area of something like 16 square meters, Because we have not, by the way, covered the whole of the mini ICAL layers with fully with detectors. We initially, to start with, we had only 2 meter by 2 meter in the center. Now we have another set of 2 meter by 2 meter, but on the central part of the detector. So leaving out the 1 meter on each side, you have a 2 meter into 4 meter gap. Each of these gaps, 10 gaps, and we have now 2 RPCs in each one of these gaps. So this was taken, I think, in the earlier phase where we had only 10 RPC detectors, and you can see the muon's flux as a function of the momentum of the muon, and this is the behavior for mu plus, and this is the behavior for mu minus. You can see slightly more muons by about 20% or so more mu pluses as compared to mu minus, and so this is something that is part of Apurva Bhatt's thesis, PhD thesis, who was an INO graduate school student. Okay. We then decided to see if you can enhance the capability of the ICAL detector by putting a veto detector around it. And so, of course, you have to start small. So we started with some building a small piece of apparatus with the INO graduate school students. And it turned out to be a very pleasant experience and also gave a pleasant surprise. So the idea is that you take a muon trigger, which consists of layers of plastic scintillator operated in coincidence and with lead in between them, so as to make sure that you don't get too much of gamma scattering, which would trigger coincidences. So you make sure that these are actually muons, and then you can also increase the threshold and that, so you can make sure that indeed they are muons first. And then you surround this muon trigger on all 5 sides. Of course, you need not cover up the lower side with the plastic scintillator, because there are no muons coming from below the earth. There are only neutrinos. Okay, so 4 sides, and the top we covered with 4 layers of plastic scintillator. Scintillator that was basically we could lay our hands on in the laboratory, existing there since many years, since Fermilab days, when the PFR group contributed a significant part of the detector in the D0 experiment. So there was some plastic scintillator lying around. There were wavelength shifting fibers and the photomultipliers. So we put it together. Basically, the students put it together with some help from our technical staff. And we were surprised to find a veto efficiency of 99.98%. And this even got, since the result was, as I said, a pleasant surprise, I had not expected more than about 99%, but I was wrong. And we even got it published. So the 3 students are the first authors, graduate school students are the first authors in this paper. This then motivated a proposal to build a CMVD, because in the meanwhile, we had learned that Fermilab was already building such a detector for the mu2E experiment on a much larger scale, on a scale of about 20 meter by 6 meter by 6 meter, and a 4 layer and 2 centimeter thick, etc. So we got in touch with them immediately, and they were kind enough to lend us plastic scintillator. Then, of course, that is what is happening now, in that we are building this cosmic muon veto detector of the mini ICAL, and you can see a picture of this assembly of such a part of this veto detector. This is engineering a picture of what the scintillator veto detector would look like, possibly. It consists of, actually these numbers are slightly wrong, but just take it as an order of magnitude. Actually, they are about 4.7 meter, but let's take it of the order of 5 meter by 5 meter by 2 meter in height, and there'll be 3 to 4 layers depending on. Anyway, it's a modular in construction. We can put 3 or 4 layers of the case maybe in our studies of plastic scintillator, which also we have 2 varieties, 1 centimeter thick and 2 centimeter thick, and there are 2 WLS fibers going through a 5 centimeter wide scintillator, extruded scintillator, and these are about 1 mm or so in diameter, 1.2 mm diameter, and then they are looked at by silicon PMs at either end. So they will tell you whether charge particles of the muon pass through this plastic scintillator. So we hope to get a muon efficiency of about 3 nines, 99.9%. We'll see what happens. this is getting built now. So if you have a chance to visit the transit campus, please do so and interact with the people there. Okay, then after this, we are going to build the 700-ton engineering prototype ICAL detector, which is be about 10 times larger than mini ICAL, but still about something like let's see, about 25 times smaller than the 17 kiloton ICAL model. It will be 8 meter by 8 meter by about 2.3 meters with 23 layers of soft iron, and it will have 20 layers of RPCs, because that is what we have procured, and this hopefully will happen in the next few years or 2 to 3 years from now. This is a pretty, the final ICAL will be a pretty tall structure, so we have made a trolley for insertion of these RPCs. In fact, there's also work going on for a robotic device that will be able to slip in these RPCs in the gaps. This 8 meter is actually half of the ICAL module in terms of length of the road, and so this will give us a very good idea of how easy or difficult it will be, and we will learn from this experience of putting in RPC detectors and filling them out. I think this is probably one of the last slides. No. Okay, what will we do at ICHEM? We will build, of course, this layer with these plates. We will also try out a slightly different approach in some of the coils, copper coils. Namely, instead of a U and a C, we will have 2 C's, and actually there should be 2 I's, and then try to see what is the performance. The number of brazings also will of course increase by a factor of 2, but given the skill which these experienced people displayed, it is this is something that we could try out, because this makes carrying the conductor in the tunnel much easier, because the C's and the I's can be put in a truck and just carry. With the 8 meter wide C or a U, sorry, it will be a slightly tricky thing. It could be done, but it will be slightly tricky. Okay, this will also give us some experience on a low conductivity water closed loop system, a closed loop gas system, which is much bigger. It will also enable us to learn about how this special trolley works, robotics for insertion extraction of the RPCs. There will be a much larger data handling system. So it will give us a feel for what are the things to come when ICAL is actually assembled and gets going. The ICAL will measure about 6,000 muons per second, about 3 kilo muons per second of each variety, slightly more muons, mu pluses than mu minuses, and it will measure them at a near equatorial latitude, something that has we only have got a measurement at mini ICAL and perhaps some earlier measurements as well. But this will do it with much better statistics for both mu plus and mu minus separate in this region of energy. Perhaps it's slightly larger for certain angles, which are 45 degrees or 60 degrees and so on. And this will also help sharpen the atmospheric mu flux calculation, which have already been carried out by one of our colleagues, Sajjad Datar, in collaboration with a doyen of the field, Honda from Japan. So this will help sharpen these calculations. It will also validate the simulation and reconstruction software using stopped muons. And finally, as I said, the method of getting the B field internally in the iron is an open question, and we will explore the possibility of this method, the muon spin rotation technique using stopped mu pluses in the iron. Okay, these mu plus muons, yeah, I'm over time now.
No, just time. Will you take another 10 minutes? Or
no, not 10 minutes, just a few minutes, because I'm almost to the end.
All right.
So the mu plus, mu measurement, mu minus measurement separately, which we can do with this engineering module of ICAL, these will complement and add new information to the GRAPES 3 data. There is already a large array at Ooty, which is taking data and which has produced some, at least a couple of quite interesting results, such as a result related to weakening of the Earth's magnetic field due to a solar storm, a geomagnetic storm. This is reported here. Due to the weakening of the magnetic field, the cosmic flux increases, and you observe a small increase in the muon flux of the order of about 1% or so. Similarly, when this weakens, then you get more of these protons coming in, and perhaps we might be able to complement this observation that has been done already. Also, WAVES 3 looked at the voltages involved in thunderclouds, and in fact, they got a number from some of these measurements, which was, I think, 5 to 10 times larger than what was speculated earlier. And this problem, by the way, has its origin in some work that was done by Benjamin Franklin about 200 years or so ago, 200 to 300 years ago. So it's addressing an old question, but with a new technique, completely new technique. And so they were able to get voltages of the order of gigavolt in these clouds, which was not heard of hitherto. And they could see that this, the flux changes are there in terms of direction, because it's related to the cloud movement across the sky in that region. And for instance, what they saw was a dip in the muon flux. And since mostly you have slightly more muons, mu pluses as compared to mu minus, it actually, the signal is a sum of two things, one of them which lowers it and one which increases it slightly. So it actually is an attenuated signal. We will see a larger signal if we see mu pluses and mu minus separately. So if there happens to be a thundercloud in that area, we should be able to get complementary information to this, but in some ways unique, because we can measure mu pluses and mu minuses separately. Okay, this will allow better up-down discrimination, and possibly, of course, there is some debate on this, but it's possible that maybe you can get identification of upgoing atmospheric neutrinos at the rate of something like once in a month or two. Okay. If ICAL becomes possible at the Pottipuram site, which I hope it does, then ECAL can be a test bed for large-scale testing of RPCs, because you will need 30,000 RPCs and over a period of 3 years or so. So of the order of 300 per week is something which is possible to test, and this will provide a test bench for that. Of course, there will be spin-off once you produce large number of RPCs. Some of them could be used, for instance, for tomography of reactors, volcanoes, hillocks, which is used in archaeology. And of course, it will help train students and scientific staff for the eventual ICAL. This I will not talk about, because these spin-offs, I think, are going to come. I will just mention it here in my slide. And since I'm already exceeded time, let me thank you all for the patience here. And I'm open to questions by you.
Okay, thank you. Thank you very much, Professor Datar, as usual, for your very nice and at a level that we all understand, very beautifully explained the entire experimental aspects and details about the INO projects. Okay, there's a question.
Shall I unshare right now?
Yes, sir. Okay. Yeah, you can unshare.
Let me see. Pause share. No, sorry. Stop share. Stop share.
Yeah, this question is from Gokula Prasad. It says,
yes.
You said that there is a problem in the measuring of interior magnetic field. Why can't we use Hall sensors to measure them?
No, so the Hall sensors can only be put exterior to the iron. You cannot put it, let's say, in the lattice of iron, right? The muon sees an internal magnetic field at the atomic scale, right? So how do you get that? And that, as I said, is an open problem. If the mu plus, the stopped mu plus, which eventually sits in an interstitial site in the iron, can be used, it's not clear that that method will work. But if it works, then it will sample the interior magnetic field. And so that might provide a handle on the interior magnetic field. Okay. The Hall probe only probes the field in the gaps, which you have to intentionally provide.
Yes, sir. So I hope that's clear to the participant. The next question says, as others are using big detectors, Japan is using water or any other materials to detect the neutrinos. How did we come to thought to use magnets or iron for our observatory? And are there any other ways to detect neutrinos?
Okay, let me first of all say that I hope it has been said somewhere, but if not, let me first of all say that this idea of using a magnetized calorimeter is not, this idea didn't evolve here. It didn't begin here. It was actually an idea that evolved in Italy, and they were actually thinking of building a 32 kiloton iron calorimetric detector, albeit of a slightly different design, 8 centimeter thick plates and so on, but using RPCs. So that project did not get funded for reasons that we need not go into right now here. But we thought that seems to be a very nice idea, because nobody has built a magnetized detector for atmospheric neutrino. And therefore, once you build a magnetized detector, you can distinguish mu mu from mu mu bar. And that's how we latched on to this idea of building a magnetized calorimetric detector. Now, once you say that you want a magnetized detector, you can say that, okay, why can't you just make a solenoidal magnet, for instance, using maybe some other material, some even material which is even cheaper than iron, let's say sand or something, God knows what. Okay, but then the problem is that you would have to use a superconducting magnet, and superconducting magnet needs low temperatures. So the cooling system for such a huge magnet would be huge. So, the experts told us that don't even think of it. Make a room temperature magnet with iron. Okay, we indeed had, just mooted this possibility, but there are experts who have been working with magnets elsewhere, and they just said nothing. That was just too complicated technology. So the other possibility, which I don't know whether you may have that in mind as well, is to use permanent magnets. But yes, there are permanent magnets, and nowadays you get pretty high field permanent magnets. But the problem with them is that, again, the same thing. You don't know what is the magnetic field. So there'll be a range of magnetic fields, which, when you get hundreds or billions of pieces, there'll be a range. They are also very expensive as compared to iron. It is much easier to magnetize iron than to make a permanent magnet and over this kind of volume. Finally, of course, if you have a permanent magnet, it's not at all easy, if not impossible, to change the direction of this magnetic field, because you would have to reverse all of these pieces. And whereas in the case of electromagnet, it's trivial. You just change this sign of the current. That's all. And there you have a magnetic field which is opposite. And that's, by the way, very useful for looking at systematic effects. Any experiment is plagued with systematic effects. They may be very important, they may be less important, they may not be important. But certainly, an experimenter has to deal with systematic effects. And one of the things that you could do is to reverse the magnetic field and see if you get the same results. Okay? And this is something that you can very easily do with electromagnet. And as I said, iron is the cheapest ferromagnetic material.
Okay. Thank you, sir. Very nice and detailed explanation. This is a very important aspect of ICAL and connected to the magnet and magnetic. Okay. So since we are running short of time, I suggest that we stop this, close this particular talk at this time. And we would again have time anyway towards end of this today's program at 3:50. So we will have to take a break. So now that it is 10:47 already, so we must we will get back at 11 o'clock sharp. Okay, and we will have Jones Panicker's talk on spin-offs of INO Project. So thank you very much, Professor Datar.
Thank you,
Vivek. This
yes.
is again. I have a small question.
Can we do it privately, because they have a break now for tea or whatever?
Yeah. Just one question. Regard. This is a technical question. This regarding this iron calorimeter. If we see this proton decay experiment is also used the same active material, right? Iron.
Yes.
And here also we are using the ICAL is iron.
Yes.
So using is there any for the proton decay and this?
Oh yeah, sure. This can also look for proton decays. I didn't mention another thing that, namely the so-called anomalous KGF event. This can also throw light on that, because it's a much bigger detector than the KGF detector. So yes, it can certainly look at proton decay. It can also look at the anomalous KGF events.
Anomalous, what is it? Can you say it again?
The anomalous KGF events. events that seem to originate in the gap between the KGF detector and the walls of the mine.
Okay.
So
That's
there
wonderful.
are a handful of such events. And in fact, Professor Rajshekharan and Murthy have written about it. And but one can, take an experimental point of view that whatever is the cause of that, we don't know. But certainly we can find out if those events also come about in a detector such as this, because it is much bigger. The amount of air in the gaps between the detector and the walls is much larger in volume, and therefore we should have many more such events. And so within a few years of running, we should be able to tell whether what was seen is corroborated or not.
So through this, my humble request to Raja sir is, sir, if you could able to take a more technical oriented detector from the detector's point of view, regarding the physics and things, a detailed, and without time bound, that will be very nice, sir. I hope Raja sir is listening to it.
Yes, he's probably listening to it, but he's muted. Maybe you can ask him in the chat box or something.
Okay. Sure.
Yeah. Okay. Thank you.
Thank you very much.
Jones, are you there?
Hello. Hi. Can you hear me?
Yes, I can hear you. Can you share your screen? Can you share your screen?
Yes, I'm doing it. Can you hear me clearly?
Yeah, a little louder is better.
Okay. Is it better now?
Yes, it is better.
Can you see my screen?
Yes,
Okay.
we can see your screen, full screen it is.
Okay. It's clear,
So
right?
I will, yeah, sure. Just give me a second. Yeah, so welcome back to the second session or second lecture for today's event. So as I already introduced you before start of the event today, so this talk is going to be given by Jones Panicker, one of our graduate students, jointly with Krishnamurthy, who is a scientific officer who works on detectors at IHF campus. So the title is Spinoffs of INO and benefits to the local communities. Since I already introduced the theme of the talk, and let us straight away invite Jones for his talk today.
Okay. I'll start. In case the voice is not clear, please stop and tell me. I hope it's clear.
Yeah, right now it is fine.
Okay. So the topic I'll be presenting on is spin-offs of INO and benefits to local communities. So by spin-off, we mean side projects of INO. So the main purpose of INO is the physics experiment, and that you all have heard from the previous speakers. So that's the main part of INO. That is why INO is built. But there are some side applications to us, to people, and that I'll be talking about. And the benefits to the local communities where INO is going to come. Pottipuram Research Center is going to come, the locality. So I'll start. So these are the topics in short. First one is advances in engineering. So basically, we are trying to push the limits of engineering so that we can have more finer technologies. And we are doing that for physics, but it's actually helping engineering in India. Second topic is the economic impacts of INO, how INO is going to boost the local economy. Third point are the spin-off projects of INO itself. And fourth is about the science education and how INO will act as a top university, which is training the people in the locality and in India in general. So I'll start. First, mini ICAL. I'm sure you have heard of mini ICAL by now, mini iron calorimeter. It is a detector that is right now operational in Madurai, IHF Madurai. So mini ICAL is a detector that is completely made in India, you could say so. Almost everything of mini ICAL is made in India. And you can see this, the detector is behind these people. These people, most of them are students, some of them are professors. So mini ICAL was made by these people, like mostly engineers, professors, students, technicians, contract employees. They are all from different institutes in India, from all around India. And mostly, like most importantly, the students from different colleges near Madurai, near the campus in IHF, they were heavily involved in this detector building. More than 100 students from different colleges were in this project. So there are colleges such as MKU, which is nearby, Madurai Kamaraj University, Jayaraj Annapakkiyam College, Periyagulam, Kalasalingam University, Virudhunagar, SVN College, Madurai. So these colleges all were involved in building this detector. So this is a particle detector. It is always recording the live track of muons that is going through the detector in Madurai. So it is basically measuring the number of muons coming from different angles all the time. So before this detector was built, there was another detector in a nearby building in this room, in a nearby room, could say. It's called A block. there's another block. This is B block in this campus. There's A block. There was another stack. So that stack was also built by students from nearby colleges, such as Arulandar College, American College, etc. So the idea is that the entire detector, this is a world-class particle detector, a muon detector that is recording the tracks of the muons all the time. It's made by students and professors, engineers in India, sourcing materials from India. So, so this mini ICAL, you can see the detector. It's a pretty big detector, but still it is 600 times smaller detector compared to the actual ICAL, which is to be built in Pottipuram Research Center. So this detector brought together different streams of engineers: electronics engineers, electrical engineers, mechanical engineers, civil engineers, and programmers, computer science engineers. So all of them came together. So this is a multidisciplinary project. So it's bringing together engineers from different streams and trying to make something that is optimized in various areas. So this is really pushing the engineering in India to the next level. So I'll go through a little bit depth, like parts of it. So in terms of electronics, in India, we had to develop low noise, low power consuming electronics. For example, in the bottom left image, you can see the two black squares. The one on the top left, like this one. So this board, this triangle board is called the DAQ board, Data Acquisition Board. So this board itself was designed in TIFR, Mumbai. And in the board, you can see the ICs, integrated circuits, chips. So this black chip on the top left, it's called a TDC, time to digital converter. Its job is to measure time very accurately, very precisely. So in this board, the TDC that is used is actually not designed in India. It's designed in CERN. It is called HPTDC IC. So in the beginning, that's partially how we start. But afterwards, we plan to. We already have a TDC that is designed in India. So that's what you see the paper on the right side, a flexible 18-channel multi-hit time to digital converter. That is TDC for trigger-based data acquisition systems. So this IC on the right side, the paper, it's designed in India in IIT Madras for the purpose of INO. We are making a silicon-based chip. We are designing a chip in India for this project. So this is indirectly helping push the semiconductor design for INO. So another thing is this Anusparsh, the first point here. Anusparsh is a low noise, fast discriminator IC developed in BRC. So this also, at the moment in mini ICAL, another IC developed in CERN is being used. So that will be replaced for the actual ICAL by a made in India IC. It's called Anusparsh. Fast discriminator, I'll just quickly say what it is. So discriminator, what it does is, it will convert a signal such as this. So this is a signal that comes from RPC, resistive plate chamber. And there will be a threshold kept. And once the threshold is crossed, it will give the output signal will be a discriminated signal. So this is what it is doing. So a low noise, fast discriminator IC called Anusparsh was also developed at BRC. The other parts, some of these parts were described a lot by Professor Datar. So the magnet, you saw the pictures the previous one. It was designed in BRC Mumbai. The magnet power supply, it was designed in VECC Kolkata. The mechanical and civil engineering, it's completely done in-house in ICHEP Madurai. So this is a INO collaboration map. You can see there are institutes from all around the country, from north, south, everywhere. And there are more than 20 institutes in India and more than 100 engineers and scientists. Apart from the students, there are more than 100 students also. So the whole idea is that we are making something in India, sourcing materials from India, having the talent from India and developing and training the talent so that they can do like even better experiments. So the next point is the industry interface for mini ICAL. and in future for ICAL also. The idea is that if we are making something in India, we need to buy the things from India. So the glasses and RPCs, about resistive plate chambers, it's made of glasses. So that was made in Saint Gobain factory in Chennai. So the picture, you can see the Saint Gobain employees along with INO collaboration member. They are testing the RPCs if the resistivity is correct as it's supposed to be. So this glasses and RPCs are made in Chennai. The PCBs are made in Arising Electronics in Bangalore. There's also another company, PCB Power in Ahmedabad, where prototype PCBs are made. The gas systems for the RPCs to work, there's a special mixture of gases that's used. So it has to be mixed correctly in the correct proportions. So the gas system was made in Mumbai by Alpha Pneumatics. Chilled water system by Entech Engineering, Bangalore. The iron was sourced from SR Steel, Surat. So this was all done for mini ICAL. And when it comes to ICAL in PtRC, again, all the materials has to be sourced, and this will flow money. So moving on to the INO Pottipuram Research Center's economic impacts or jobs created. So the project budget was 1,583 crores. So this is the old budget. The revised budget will be higher. It will be higher than 2,000 crores. So the idea is that the money is going to flow to the people. We need to buy supplies and materials worth 568 crores as per the old budget. Then there is civil, electrical, mechanical, road construction works, water, all this together 470 crores. So all this is going to provide employment to people, providing business and job opportunities. And there'll be also jobs created during the construction. And in INO FAQ, it's written that the construction contract will specify that local labor should be used based on the skill levels to the maximum extent possible. So this is during the construction. And after the construction, there will not be that many jobs, but still there will be some jobs. Gainful employment will be there for a small number of people by way of sourcing of services and daily needs for INO. It's to maintain the INO PtRC facility and for upkeep of the buildings and so on. So this is also going to create jobs. Basically, this much amount of money is going to flow into the project, and that will be distributed, and mostly the locality will be the people benefiting, mostly. So along with the construction of the lab itself, naturally, we need to also develop the locality so that the accessibility to the lab is improved and so on. So these were the plans back from 2015 on developing the nearby roads and infrastructure. But now the project is delayed, so new plans on infrastructure developments will be made based on the present day needs. Okay, so this picture is from of Kamioka town. So Kamioka town is now famous for Kamioka Observatory. I hope you have heard of Kamioka Observatory before. It's famous for this neutrino detector called Kamiokande. In the beginning, in 1980s, they made this detector called Kamioka NDE. So NDE stands for Nucleon Decay Experiment. Nucleon Decay Experiment. I hope it's clear. Kamioka NDE. Okay. So this was an experiment from 1980s. Then later they made a newer experiment called Super Kamiokande, which won the Nobel Prize in 2015. And after that, now they are building a newer detector called Hyper Kamiokande. So the story is that this Kamioka, it was kind of a village, and it's in a very naturally beautiful place, very similar to how Pottipuram, the locality is. Still, it's very sustainably built, and you would not even know that there is a nearby underground neutrino observatory in this town. So people are living very peacefully with development, and it's like an integrated development. Where after the Kamiokande observatory came, the place got into the world map, and it got more developed compared to before. Okay, now I'll move on to the next section in our presentation. It's the spin-offs of INO, possible spin-offs of INO. So first topic is RPCs for medical imaging. So there are applications of physics or experimental physics in medicine. It's very clear. Maybe the best example is X-ray. We have all used X-rays at some point in our time. It is physics basically. But there are more advanced applications sort of. So one of the application is something called PET scanning, PET. So PET scanning stands for positron, this PET here. So PET stands for positron emission tomography. So positron is the antiparticle of electron. Okay. So overall, the idea of the scanning is simply that the patient will be injected with a radioactive compound, a radioactive molecule. It's a glucose actually, but that glucose is modified so that it is radioactive. And that radioactive molecule, once inside the body of the patient, it will go and accumulate in where there is a tumor, for example. So it is to scan for tumors inside some cancer patients. This is the common application of PET scanning. So once that radioactive molecule is injected into the patient's body, it will go and accumulate in the tumor site, and it will start decaying. It is a radioactive material. So that will decay and it will emit a positron. Okay. So over here, so this is the original nucleus, positron emitting isotope. So that will emit a positron. So that positron is going here. Okay. It will also emit a neutrino, but that neutrino is not important for our case. We are not detecting the neutrino for PET scanning. So that positron will find some electron. So in our body, in the patient's body, there are many electrons, and our positron will find some nearby electron very fast, and it will annihilate. This is a matter and antimatter annihilating together, and it will give off two gammas. Two gamma means two photons. So those are these photons. So there'll be the positron and electron will annihilate and give two gammas, one going here and one going here. And around the patient's body, we'll keep photon detectors. So the idea is that we'll try to detect this photon from opposite sides. So if we can do that by drawing a line between the two places where the photons were detected, we can find from where this positron came. Okay. So this is how we scan. So here, what INO can do is, so INO has already made this resistive plate chambers, RPCs. So RPCs are very good for detecting particles called muons. But with some modification, we can make something, we can make a modified RPC which can detect photons very efficiently. Not very efficiently, but it can detect photons. Okay. The advantage is that by making this modification, it's called multi-cap RPC, we can improve the timing resolution, or how accurately we can say when the photon was detected. So the importance of this is that, let's say that we have a detector here, detector D1 and detector D2. And this detector on top, this photon came at time T1. And for the detector in the bottom, it came at time T2. So if we can measure the time difference T2 minus T1, so we can know where along this line the photons came from, or the annihilation happened, or where the positron was. For example, if the annihilation happened in the middle, T1 and T2 will be same. If it happens somewhere closer to this side, T2 minus T1 will be positive, and negative vice versa. So this is the idea. The idea is that we can use the RPCs by using a small change, so that we can very accurately measure the time and thereby we can use it for PET scanning. So PET scanning is a technology which is already there, but the problem is that because now the detectors are expensive, the PET scanning itself is expensive. There are other reasons why it's expensive, but detector is one of the reasons why PET scanning is expensive. So by using multi-gap RPCs, we can make it cheaper. Okay, so some of my seniors have worked on this multi-gap RPCs for PET scanning. So first paper, the top paper, design development performance study of 6-gap glass MRPC detector. MRPC means multi-gap RPCs. So this paper is from 2016. Okay, so this paper first studied the performance of a 6-gap RPC. So the idea here is that I'll just quickly say this also. So usually our RPCs are like this. There are 2 glass plates, and in between there is a gap. The gap is about 1 mm or 2 mm. So the idea is that in the previous slide I said that we need to measure the time very accurately. So that brings the question of timing resolution. So the timing resolution, if this gap is more, the timing resolution will be poorer. If the gap is less, the timing resolution will be better. So in multi-gap RPCs, what we'll do is we'll divide one big gap into smaller gaps. There will be smaller gaps like this. So in this paper, top paper, 6-gap multi-gap RPCs are tested. So with the smaller gaps, the timing performance will be better. Okay. So first, this was done in 2016. Then in 2019, the paper in the bottom, I think it's from 2019 or 20. It's feasibility study using the multi-gap RPCs for PET. So this is a preliminary study to see if we can use multi-gap RPCs for PET scanning. So this was done by Mohammed Nizam. He's also a senior of mine. They have this preliminary work. Now we need more research in this field to make this into a product that can be used for PET scanning, like in commercial applications. Okay. So again, one more applications with RPCs. This is with regular RPCs, which we use as muon detector. So RPCs can be used for something called muon tomography. The idea is that there are naturally occurring muons, such as you can see it coming in this picture. So this is a pyramid, by the way. So this idea was tested in 2017 to scan the interior of a pyramid. The idea is very simple. We'll keep the muon detector outside or inside some object that we have to scan. And naturally, there are muons coming from all the sides. So when these muons will come, it will go through the thing or object that we are scanning, and the muons will reach the muon detector. So by looking at the number of muons coming or the energies of the muons coming from different sides, we can see the inside of the material that we are scanning just from the naturally occurring muons. All we need is a muon detector. So using this technique in 2017, they found a void, a gap, sort of inside the pyramid, which was previously unknown. So this is a proven technique, and this has applications in security. For example, scanning trucks or heavy shipments that will be coming. So this is a very, very useful field and very upcoming field. Very useful. This here RPCs can be used, and it will provide a cheaper solution for muon tomography. So so far, no one in INO, as far as I know, has worked on muon tomography directly for applications, but there was an unexpected discovery, so to speak, when one of my seniors, Dr. Peturaj, he was trying to estimate the muon flux in Madurai. This picture here is ICHEP campus in Madurai. So this is ICHEP campus. Okay. So the idea is that in this room here, there is a muon. There was a stack of RPC detectors. So a stack means it's like this. So there were 12 RPCs stacked like this. So the project or his work was mainly to just measure the number of muons coming from all the sides. So there will be muons coming from here, here. Muons will be coming from all the sides, like here, like this. So what happened was, Dr. Petulaj, he was trying to measure just the number of muons coming from all the sides. And it was observed that from this side, the number of muons that came, it did not fit the observation. It did not fit the expectation. So there were an expected number of muons coming from everywhere, but the observation did not match the expectation coming from this side. So later it was understood that because of this building here, this building over here, I hope you can see this building. Because of this building, the number of muons coming from this side was different. So accidentally, he was scanning this building by having a detector in this building. The source of this radiation is just natural. The muons are always coming. All we need to keep to scan some object based on its density is we just need to keep a stack of RPC detectors. Or basically we are looking at we need muon detectors and we can use RPCs for this purpose. Okay. So this is moving on to the last topic about science, education, and so the biggest purpose of INO is that ICHEP. ICHEP is Inter-Institutional Center for High Energy Physics and Pottipuram Research Center. The main purpose is that it will be a world-class university. It will attract the best scientists in the world. It will train students in the best technologies and science in the world. So this is the biggest advantage. This is why we should make INO, ICHEP and PtRC. So this picture is that of Dr. Abdul Salam, Nobel laureate from Pakistan. This is him visiting KGF lab, Kola Goldfield underground lab in 1980s. So this was what KGF had done in India back then. The KGF lab, neutrino experiments and nucleon decay experiments, proton decay experiments. So they attracted the world's best scientists, and INO is here to restart that leverage that we had, that advantage that India had. So PtRC will attract the best scientists in the world. This is a part of, again, science and INO being a university. So INO already have had this INO graduate training program. So I am a student in this INO graduate training program. Already 31 students have graduated. And these students are either working in top experiments around the world or some are working as professors in top universities. And among the students, there's also a very good representation of women scientists. So that is also something INO is very proud of. INO has also been consistently involved in outreach activities, mainly with nearby colleges visiting the campus in ICHEP. So all this is done in ICHEP in a transit campus. This is a temporary campus. The actual ICHEP campus is going to come near here, a few kilometers from here. So with that actual university coming in Madurai and a lab PtRC coming in Pottipuram, it is going to like boost the science outreach activities even more. So whatever is being done so far is in limited facilities, sort of. This is another outreach activity. This was during the solar eclipse in December in 2019. So many people came to Madurai. I was not here, but many people came here to see the solar eclipse. The glasses were distributed. And so these are the photons. It was not a complete annular eclipse in Madurai. in Ooty, it was a complete annular eclipse. I was lucky to visit Ooty that time to watch the complete annular eclipse. Okay, so I'll end with this slide. So this slide is from a plan presented by District Collector in 2010. So back then, a part of INO project, a modern science park was also proposed, and it was even allocated a site. But all this is from back in 2010, and the project was delayed, and all the plan was delayed. So hopefully everything will catch up soon, and we'll have something like this, I hope. That's it. Thank you. We can have questions. Hello. Hello, you can hear me, right?
Yes, we can hear you. Students, is there any questions? There must be some questions. You can ask or you can type in the chat box. Okay.
Hello?
Nice. Hello, Satya.
I'm looking at the. Are you looking at the questions?
Yeah, I saw one question now.
Okay.
I think only the last question is.
Yeah. That are you going to answer that, Raghav Krishna?
Okay, I think I'll answer, but if I am saying anything slightly wrong,
you can start and others can pitch in. There are two questions now.
okay. So is it possible to do dark matter research at ICHEP? I think for dark matter experiments also we need low background environment. So at ICHEP means ICHEP is a institute that is on surface. It is not underground. But at Pottipuram Research Center, the underground lab, we can have dark matter research as well. In fact, there are 3 caverns, I think. The one main cavern will host the ICAL experiment. The other 2 caverns, one of them could be for dark matter research. Also, the ICAL experiment itself has some potential for looking for some specific types of dark matter candidates. Some specific types of dark matter candidates which can decay into 2 muons, one muon and one mu minus, mu plus. So specific types of dark matter searches can be done by the ICAL experiment itself at Pottipuram Research Center. Then there are smaller caverns which can host other dark matter experiments. But at ICHEP, I don't think so. I think we need underground, low background environment.
Okay. I think I request the project director Govinda Majumdar.
No. I do not need to add anything. What he told, no, those are exactly the correct answer he has given.
Okay, all right. So then there is another question. You can see, I think, right, Jones? Is there any?
Yes, I saw the question. Is there any way to harness?
Yeah, can I say something?
Yes, sir.
Let the answer, give the answer, then the question will come.
No.
He is answering the question. Oh no, Rajaji, sorry.
Rajaji wants to add.
I could not recognize the voice. Sorry, Rajaji.
Okay. I just want to add something about the question connected with dark matter research. As far as dark matter research can be done in the Pottipuram lab, I think that Vivek Datar already mentioned that the anomalous KGF events, so-called anomalous polar events, Murthy and myself had suggested that those are due to the decay of dark matter particles.
Rajaji.
Yeah.
Rajaji, can you adjust your mic, this video a little bit, please?
Oh yeah. Vivek Datar already mentioned about the suggestion made by Murthy and myself some time ago that these anomalous polar events might be due to decay of dark matter particles. And this is a suggestion. And in Pottipuram lab, since there is a lot of empty space, there will be a lot of dark matter decaying if our suggestion is correct. So our suggestion can be confronted, whether it is correct or wrong can be proved. This will be a great thing, because if it really turns out to be true, the dark matter has already been discovered in Kolar long ago in India. But of course, this is only speculation right now. But the Pottipuram lab will look for these things also. I mean, automatically, we have to make some other extra detectors. But with that, we will be able to either prove or disprove our speculation about that.
So, maybe Professor Datar can add a little bit about the INO initiative.
Okay, can you hear me?
Yes, yes.
Okay. No, so there was some effort going on. I don't know the exact status of that right now, but there was an idea that cesium iodide detectors could be used cooled down to liquid helium temperatures, and I mean even actually with dilution refrigerators down to millikelvin temperatures, 10-20 millikelvin, to look at the both the thermal signal as well as the scintillating signal, and thereby look for dark matter. So the dark matter, which is supposed to be all over the universe, will typically have velocities of a few hundred kilometers per second, and then that will recoil against the cesium and iodine nuclei to produce signals due to these recoils. And those will be detected in two ways, so as to discriminate between backgrounds. So there was a move to do that. And in fact, the cesium iodide has been something that has been developed in BRC. And now that technology is actually transferred to ECIL, and they are making detectors for general purpose. So, the only issue is that it would have to be purer radiologically. It should have very small amounts of radioactive impurity, if at all, as compared to what they are at present. And so that is something that I think some set of people are working on. But by the way, the detector development can also take place at ICHEP. Although you may not do the experiment there, but the development of detectors can take place at ICHEP.
Okay, sir. Thank you. Thank you very much. And so the other question is there any way to harness the energy of neutrinos for free energy other than what people are doing at neutrinoenergy.com? Okay, so this is a question. Okay, so Jones, you want to start, and then probably
I think I will start, but I'm surprised actually.
No, there is no surprise about it. This has been on for many, many months and years. It is very difficult to kind of explain by the kind of physics that we know of. So it is better that we make less comments about this particular initiative and what is being projected on the web pages. But if any others really want to add, maybe Govindo or Professor Datar want to add, it's fine.
I'll just say something.
Please.
See, the neutrinos that we are detecting, atmospheric neutrinos, they have energies of the order of giga-electron volts, one neutrino. Okay. And giga-electron volt, 1 electron volt is around 10 raised to minus 19 joules. It is a very, very small unit of energy. So even though we call high energy neutrinos, actually the energy of one neutrino is very, very small. And just thinking about how many neutrinos we are detecting in INO, in PtRC, every day, even with such a big detector, we are able to detect just 3 neutrinos, 2, 3, 4 neutrinos. By harnessing that much energy, we cannot get any useful energy, like 3 neutrinos of 10 raised to minus 19 joules. Not 10 raised to minus 19 because of the GeV factor, it will be 10 raised to minus 10. But again, it is a very small amount of energy, and it is very difficult to detect neutrinos anyway. So I don't think there is any question of harnessing neutrino energies, in my knowledge. But Yeah, I'm surprised that there's a website like that. So
Yeah. There are lots of things happening on that side, Jones. But that's why I said I think see these are there are many speculations and many such things go around. But unfortunately, you put it in a proper perspective. Okay. So anybody, Professor Datar or Rajaji?
Yeah, I could comment on this. I think one can even make a stronger statement saying that this looks like somebody who is trying to fool the public and get some money out of it. Because there is no way the neutrinos that we have in nature can be used for producing energy. We know that neutrinos are part of the processes that occur in the sun that lead to energy production, but that is by way of photons that come on the earth. So solar energy is of course very useful and we can harness it for use here. But neutrinos are some of the shyest of particles. There's no way you can harness them. And why would you want to do that when you have much more, much better ways of doing that? And when I say much, it's not by a factor of 10 or 100. It is by a factor of 10 to the power of 10, 10 to the power of 12. So this is just probably a set of people who are con men or whatever persons who are fooling the public into investing money in this. I think a much stronger statement should be made in this matter.
Yeah, good. Actually, I was hesitating, sir. It's nice that you actually made that statement. So please be aware of many such things. Of course, in the name of science, quite a lot of such speculations go around in the world of social media and WhatsApp and whatnot. But one has to kind of know in a proper perspective that Jones as well as Professor Datar mentioned about it. Okay, so we must move on to a more probably useful questions. How can a normal engineering student can apply for internship or fellowship? Jones, can you see this question?
yes.
Okay, please go ahead.
For doing research in India in general, I think okay. This question is about research in general in India or about neutrino physics?
No, this is, I think, in the context of INO. So they're asking if there is any, we only talk about most of the time science students. Are they also equal opportunities for engineering students who can apply for internship in INO?
Okay, I think previously there used to be, I mentioned about INO GTP, Graduate Training Program. So INO Graduate Training Program, I'm coming from a BTech background. I'm an engineer, electronics engineer, as of now. So BTech students were also eligible for INO GTP. So to get selected for INO graduate.
We can't, Jones, we can't hear you. Can anybody hear him or moving?
No, we can't hear him. I think either he has lost his connection or there's a problem in the video audio, both.
Yeah, connection is on, but somehow I'm stopping his video so that, no, even then, yeah, he has now lost the connection. Let us, by the time he comes back, let us take up a few more questions.
His video seems to be on.
Now he's back. Now he's back.
My data had exceeded the today's limit.
Okay.
So so there is TIFR GS exam. That's something I think students should write. Then there is JEST exam, JEST. So this exam also in BTech engineering students are eligible for it to continue research into this field. Then I think net exams and what else is there I'm not sure. Then through GATE also, GATE physics as well as GATE physics or GATE engineering. There are works because projects such as INO or any science project, everywhere there is use for engineers. Engineering is part of it. So everywhere there is opening. Yes, I'm not sure which all exams to write. So TIFR.
The question is about internship, not about so much. I mean, the question is more about internship, Jones.
Okay, I think about internship, I think Satya sir, it's best if you answer, right?
No. Okay. Let Professor Datar then.
No. I think Satya, I think you can.
Okay.
Say. I was also going to say that the question was about internship.
Yeah.
And
actually,
not about
as our Jones very nicely mentioned, he himself, his first degree is in engineering, and of course, he is now doing work related to INO, and also, of course, applying his knowledge, what he gained in BTech in the instrumentation and electronics area, besides tackling physics problems related to INO project. So, first and foremost important thing is, for the graduate students, we don't distinguish whether you are a science student or an engineering student. You crack this exam that Jones mentioned, and you crack the interview that the INO organizes, and then you are in as a research scholar. Okay, so that is one part which he has already dealt with. The second part, which specifically for the internship, yes, we had in the past and continue to have students who are trained in engineering and also in physics equally well, because only thing is their pieces of work, their field of work, the area of the work in INO will be different depending on your capabilities and your training. And let me tell you, I mean, history is full of success stories, or if I can say examples of engineers becoming the most successful physicists and physicists doing the most successful engineering work. Okay. Today morning, Professor Datar mentioned about Paul Dirac. He is an electrical engineer, right? He won Nobel Prize. I mean, the kind of work that he dealt with in quantum mechanics and, of course, in some sense, the antimatter and so on. And similarly, you have people who wrote MATLABs and whatnot. You know, these are people who are trained in physics. And, you know, the person who invented transistor is also a person who won Nobel Prize, 2 Nobel Prizes, okay, both for superconductivity and transistor and so on. So there is no such kind of a distinction. And we have, INO itself has a very famous neutrino phenomenologist by name Professor Uma Shankar, who is again engineering graduate from IIT and so on. So coming more specifically, so it is, INO itself is a very engineering intensive project. And so therefore, a lot of heterogeneous skills of engineering are applicable. It could be detectors, instrumentation, electronics, gas systems, magnet, you know, the whole of civil structures, mechanical structures, and so on. So, of course, physics starts happening when the detector is switched on, and physics also is done in simulations and trying to find the, you know, the physics potential of the INO project and so on. So it's a big heterogeneous skills that gets used in typically any modern science experiment. Let's see all the 4 experiments that if you have studied, you will see papers are written with 7,000, 5,000, 4,000 authors who are a good mix of, you know, both engineers and scientists. So you're most welcome, just like any other science student at the IHF campus for doing your internship. But as Professor Govinda Majumdar mentioned yesterday, it's just the COVID that is preventing us to call many of you. We hope that by next summer we will have opportunity to invite you. Okay. Sorry for that long answer, but I hope that clears your doubts. So Jones, the next one from Prasanna, it says, do neutrino? Yeah.
I cannot read the questions. I lost the.
Do neutrinos are similar to ether medium? Do neutrinos are similar to ether medium, and it is worth to do a research about ether medium in this era?
So actually, this question, I'm not sure if I understood correctly. I don't think ether used to be a theory in late 1800s, but after the Michelson-Morley experiment and after Einstein's special relativity came, I think ether is like completely scrapped. No one thinks that there is any ether. So, and neutrinos are just particles which exist in our space-time. I don't think there is any connection to neutrinos and ether. I don't know if I misunderstood ether. Is there some other ether which I should be knowing?
No, I think it's the same ether.
Okay. Yeah. Then there is no connection between neutrinos and ether. Ether was a hypothetical or someone's imagination to explain some results or some observations, but later experiments clearly show that there is nothing like that. That theory is completely wrong or not the real world. But neutrinos are real. Neutrinos are there. We can detect neutrinos. So the two are very different.
Okay. This question comes back again, but I hope you don't have to add any more. It says, in future, can we expect more of clean energy from neutrinos? Unless you want to. Yeah. Okay, please.
I think the future, my best expectation would be nuclear fusion reactors, ITER collaboration. ITER. There is a video on ITER in INO YouTube page itself that will explain everything. And neutrinos directly, neutrino energy, I don't think so. I don't think it's possible. But nuclear fusion reactors is a next big step to clean energy, I think.
Okay. Yeah, that's a nice answer, Jones. It is true that one of the mega science, maybe super mega science, I must say, projects in which India is actually involved, though there are still trying to build demonstrators, and there are many competing techniques as far as the fusion detectors, reactors are concerned, but one of them is being tried by the ITER, which is situated in France, but there are several countries, including India, is playing a major role. Yeah, so great. Now you have one more question. Okay, sorry. So this was actually written to me, but let me read. I don't know what the question is. I thought that dark matter would be usually in outer space and not in planets. Then how were we able to detect them in KGF? And if I am wrong, please correct me. So once again, Professor Datar or Rajaji, I think, talked about it. If he's there, he can answer, or otherwise maybe Professor Datar want to answer this.
I can just start, and I hope Datar sir will answer more. So there is dark matter everywhere, to answer that question, I think. So there is dark matter everywhere. The density will be slightly different. How do we know that there is dark matter? It's because we are looking at distant galaxies, the motion of them, and we apply the theory of gravity and try to predict the motions. But somehow there is a mismatch. The theory of gravity, and the whatever visible mass that we see there, it is not adding up. Somehow it looks like if there is some extra mass there that we cannot see, that will explain the situation completely. But actually, there is dark matter not just in the outer space, but there is dark matter everywhere, even in our room, at a different density, sort of. So everywhere we can do dark matter experiments. But like, we can have a dark matter detector here, but we don't know how the dark matter exactly interacts. But if we knew that, we can have a dark matter detector basically anywhere. Only thing is that we need low background, because there are other particles, cosmic rays, muons, etc. So we need to keep it away from them. So we need an underground, low background environment for keeping the detector. But to answer the question, there is dark matter everywhere at different densities. That's all.
The question was, since it was connecting to KGF, so I think what Rajaji just mentioned was that one of the species of events which were recorded in the Kolar Goldfields experiment, so-called Kolar events, were projected to could be a signatures of dark matter, because it couldn't be explained by any other known physics. Okay, so that was the connection with KGF. Now again, a question: will you accept research interns for dark matter research? You want to answer this, Jones?
Sir, actually, I don't know about it.
Okay. No. I mean, since we talked about the dark matter experiments called INO as one of the proposed experiments in the INO cavern or PtRC cavern, this particular initiative was taken by a group which is also, I mean, mostly people from SANP, Saha Institute of Nuclear Physics, and so on. The ICAL collaboration per se is not, of course, pursuing the dark matter research. That is, of course, difficult to do many experiments together. So in principle, there are options, but I can't immediately remember any particular person who is now ready to take some research interns. But it will be nice if you can write to the same email that I mentioned earlier, contact.us at ino.tif.res.in. Just if you go up on the chat window, you will see all those links. Okay, so let us move forward. So Jones, we have quite a few questions, so maybe you have to be a little quicker. Sir, is there any way to increase the number of neutrino interactions during the observation?
So what we usually do is we have dense detector. Basically, we need bigger detector, more massive detector. For that, we have bigger detectors and try to use more dense material. For example, I think instead of iron calorimeter, if we had a magnetic gold calorimeter, it will be more expensive, but more dense material means more interactions. And so that is the only way, I think.
The way it was mentioned as during the observation, so I'm not sure if he's saying something dynamically once the experiment is set up and running, but in any case, that is sort of not possible.
So, how I see it is like all the neutrino experiments, whether it is electron neutrino, muon neutrino, what is done is we let the neutrino come and interact with the detector. So if it is an electron neutrino, that electron neutrino will come and interact with the detector and it will give off an electron. If it is a muon neutrino, it will come and interact and give off a muon. So that probability for a neutrino to come and interact, that we can't do much about it. For a given energy neutrino, there is a interaction probability. The only thing we can do is we can increase the number of target in the detectors. Target means where the neutrino comes and interacts, where the neutrino comes and hits, sort of. So all we can do is we can increase the number of detector atoms, detector target. So have a denser detector. That's it.
Okay. There is another question. Do neutrinos interact with some unknown forces or particles during their travel through space, which leads to change in their flavor? May it be one of the possibilities behind neutrino oscillation?
Okay, so here the question is, what is the reason behind neutrino oscillations? Neutrino oscillations basically mean the initial neutrino flavor will not be the final one. Finally, the neutrino flavor will change. If you start with the electron flavor, later it will not be electron anymore. It will be a combination of electron, muon, and tau neutrinos. So there were multiple theories behind neutrino oscillations. So currently the accepted theory is that of neutrino having a mix, neutrino mixing. Neutrino mixing, that means electron neutrino does not have a specific mass. Electron neutrino itself is a superposition of 3 different masses. Similarly, muon neutrino and tau neutrinos are superpositions of 3 different masses. So this is called neutrino mixing. So neutrino mixing is the accepted theory for neutrino oscillations. But there are other possibilities or other theories which try to explain neutrino oscillations. One of them is this neutrino decay hypothesis, that let's say an electron neutrino came and later we realized that we are not detecting that electron neutrino. That means on the way it decay. So that was one possible theory. There was some other theory, I think neutrino decoherence. I don't know well enough to explain it. So there were other theories why neutrinos may change the flavor, but the theory that is accepted is that of mixing and neutrino oscillations because of neutrino mixing. That is well accepted because that's a simple theory, so to speak. There is just like in some way there is just one assumption. We are assuming that neutrinos, like flavor type neutrinos, are not mass eigenstate. We are just assuming that. Plus, we assume that the masses are not zero and small things. But with that one hypothesis of neutrino mixing, we can explain almost everything. There are lots of neutrino experiments around the world. With that one hypothesis, we can explain all the observations. We can count the number of, for example, you are starting with a muon neutrino. And you can look at the number of missing muon neutrinos. You can look at the number of electron neutrinos that appeared. You can look at it at different energies. So at every different scales of energy, whatever starting neutrino flavors, everything can be explained by this neutrino mixing hypothesis. There are some open questions also, like some anomalies, even with this hypothesis. But as of now, neutrino mixing is the best hypothesis to explain neutrino oscillations or neutrino disappearance. These things, basically. I hope that was clear.
Okay. Just there was a follow-up question. It says, do neutrinos interact among themselves?
Okay. Okay, I think they will, because see, neutrinos can interact amongst themselves. We can draw the fine neutrino scattering, for example, but the probability of that will be very, very small. I think in practical, our experiments in Earth, we don't care about neutrinos interacting amongst themselves. But I think in extreme cases where the number density of neutrinos is very high, when there's a lot of neutrinos in a very small area, and in such cases, this can happen in, I think, I'm not sure.
Jones, I'm just adding that, yeah, it is true. Recently, there was a paper within the supernova explosion that the neutrino density is very large. There, this effect is maybe visible. It is not the proof, but there is a speculation that supernova explosion time neutrino, they interact themselves. So the observation will be the different. And there the neutrino density is very, very large.
Okay, so that is the idea. There is interaction, but the probability is so low unless you have a very dense neutrino stuff. I mean, a lot of neutrinos very densely coming together and sort of colliding with each other. It can happen, as Venkateswaran said, in supernova when there is a lot of neutrino flux. But in practical Earth experiments that we do in our lab, there we don't usually consider the neutrinos. Next question, I'll go to.
Further follow-up on that. It says, is the probability of neutrino interacting with themselves is same with the probability that they interact with other matter?
Okay, I have to think.
It will be the same, because this interaction occurs through this, according to our theory, it interacts through this weak interaction W or Z medium, and that strength with this neutrino and this other particle are same. So that's why this interaction will be nearly the same, other than some space and mass matters.
But
if you look the Feynman diagram, W and Z exchange, it will be the same.
Exactly. Okay. Are there any more questions, sir? It's very nice that there's so much of interaction with Jones today, even way beyond the topic that he spoke about. Of course, there are a lot of questions on the internship opportunities and so on. Okay, so there's a comment. In fact, it's many doubts of mine are clear from this question answer discussion. Thank you all. So,
Satyanarayana, I would like to make a comment on one of the questions that was asked.
Yeah, I was about to come to you, sir. Yeah, please.
Okay. No, so this was a question. The answer, of course, given by Jones was absolutely correct. It said that can you somehow increase the rate at which the neutrinos interact with the given detector? Now, of course, that cannot happen. But you can design detectors which are more efficient in detecting neutrinos. That is possible. And for that, of course, you have to, I mean, a given detector will not be able to do that over time. But if you design a detector, let's say based on coherent neutrino scattering, then the coherence of interaction between the neutrino and various nucleons in the nucleus can lead to an enhancement of factors of 10 to 100. For instance, very recently, meaning about 3-4 years ago, coherent neutrino scattering has been detected. Of course, that happens only for a momentum transfer such that the inverse of the momentum transfer is of the order of the size of the nucleus. But when that happens, all the nucleons, the interaction amplitude adds up coherently. And so, for instance, if you have mu scattering on, let's say, a nucleus like cesium iodide or a detector of cesium iodide, it will scatter off the neutrons in the cesium, and that can lead to a factor of 100 enhancement. And this has been already observed in the Oak Ridge National Lab based neutron source, spallation neutron source. And this is also being now discussed for applying it to use of measuring reactor antineutrinos, then supernova neutrinos, and so on.
Okay, thank you. Yeah, I just wanted to come for the comments. And regarding any other questions, okay, there was nice comment. It said, thank you, sir. This was very insightful talk. So, okay, so are there any more questions from you? Otherwise, we will close this session. Okay, just give me a second, Jones. If I'll check if there are any questions from YouTube. Yeah, there are a couple of questions. Let me see if there are repeat. Do neutrinos interact with some unknown force? Okay, oh, this is the same probably. Maybe it will be thing. Do neutrino interact among themselves? I think this is the same question that you already answered on Zoom. Yeah, so I don't see any more questions for Jones. So we should really thank him for bringing up such a nice interaction among you. Someone was asking, can you please share the slides? They're already there. I mentioned to you that they are along with the videos, YouTube videos, which are there on the INO Project channel. Okay, they're already there. You can have a look at them. Okay, so if there are no more questions, let us once again thank Jones Panicker for his excellent talk. And now that comes to the end of the morning session. So we will again meet in the afternoon at 2 o'clock. And let me just quickly share the rest of the program. Here it is. So 2 o'clock, we have this talk by Dr. T. Venkateswaran from Vigyan Prasar. He's going to talk on public interaction and communication skills. And at 3:15, as you said, we have a kind of the final panel discussion with all the participants. Okay. So with that, let us close this particular session. Thank you very much for joining, and you can continue to log in if you like, or otherwise you can rejoin, but we'll have the next session at 2 p.m. Thank you. Thanks, Jones.
ஓ இதை ஆஃப் பண்ணுமா?
Hi, TBB. Can you hear me?
Hello.
Hi. Yeah. So all set, you want to share the screen? Yeah, perfect. I can see you.
Yeah, I'll check my presentation.
Yes. Yeah, I did enable your sharing. Yes. Great.
It's working fine, right?
Yes, working fine. Slides are changing. All set. So we have just a couple of minutes. So we'll wait.
Sure.
Let me start.
I'll also get some hot water.
Yeah, water. Okay.
Yeah.
Ten minutes. TBB. We'll start. We'll start in a few minutes. I'm just waiting for the speaker to come to his computer. So, PVB all set?
Yeah. So we can start.
Yeah, you can share the screen.
Yeah. Okay. Good. So, good afternoon, friends. So, let me start my presentation. I'll share my screen and then, yeah, good. So, I'm sure in the last 1.5 days, many people who talk to you about various aspects of India-based neutrino observatory, as well as what kind of research that is being proposed under it, might have also referred to some of the false claims, fake fears, which are being circulated. They might have alluded to you, right? So many of us, before knowing what the project is, were perhaps apprehensive. But after knowing what it is, sometimes we may feel that how people are so gullible. Okay, so that's a usual reaction that we get. So what I would like to do in this presentation is to talk to you about what does the research say about why people appear to be duped or gullible. What makes it? What are the forces which are acting? Plus, what can we do? Okay, so that's going to be my context. If you look at some of the fears which are circulating in social media related to India-based neutrino observatory, some fears are related to local people claiming inconvenience or discomfort during the construction phase of India-based neutrino observatory. Like there may be a lot of noise when you are going to dig up such a big tunnel. Maybe a lot of dust will come out. And maybe the nearby villages might be covered with that dust. When you are going to dig such a deep tunnel, a lot of materials will come out. You need to transport them. You cannot keep it in the same place. So when you transport, that means that a large number of trucks will be playing in the road, and that may hamper the normal life in that area. This is one kind of fears that some people express. Then there are also claims that the explosives which are going to be used for constructing the tunnel, for digging the tunnel, will cause shock waves which can perhaps damage the walls of the dam. That's another kind of rumor that is circulating. Then there are also rumors, fears related to land acquisition and restriction that perhaps may be imposed. Some people say that because this is going to be a nuclear facility, that's how they see it, 1 kilometer around that region will be sanitized like they do around nuclear power plant, and people will be kicked out. You know, this is one kind of a fear that people talk about if you go to the local area. Then there are, from a point of view of physics, students who are physics students appear to be totally ludicrous. So the claim is that this calorimeter, ion calorimeter, is going to be world's largest magnet, and maybe it will attract all the iron objects, maybe even hinges out of the door. in the nearby villages and cause havoc. Like the scene in the film Yendran, right? Something like that. Then there are people who say that natural neutrinos are okay. We are not against it. We know that neutrinos are produced in atmosphere, blah, blah, blah. Natural neutrinos are okay. What we are worried is neutrinos which are going to be produced in neutrino factories, artificial neutrinos. So they create this mistaken concept called artificial and natural in terms of neutrino, in terms of neutrinos properties, right? So, and they ferment fear. Then there are who make false claim that this whole research of neutrino is related to making bomb for destruction, nuclear weapons, okay? And then they claim that this whole project is nothing but a subsidiary project of Fermilab research. This is how popularly these are all put, okay? Then there are people who might ask questions like, are rules being followed? Is the site really within the tiger reserve? Things of that kind. Yeah, so these are all various questions and fears that people have. So let's look at slightly more closely some of these fears and views that emanate from public. We might think that these fears are essentially due to people not knowing science, and so we should be telling them science. Yes, of course. And when we are going to talk science to general public, we think the important problem in communicating science to general public, or general public not understanding what scientists are saying, is because of technical words. That is our usual reaction to such a problem when we talk about communicating science to general public. We do use technical jargons which are very specific to the disciplines in which they are used. Like, say, for example, if you are studying genetics, the words replication, transcription, and translation have a very, very specific meaning within genetics, right? So it's a technical word within genetics. But is the technical words really the problem? We seem to be using a lot of technical words in many contexts. Like, say, for example, cricket, which somebody said is the common religion of India. Yeah, we use quite a lot of technical words. When you say no ball, what does it mean? It means that there is no ball. What do you mean by off leg, offside, on leg? Okay, over pitched. Right. So these are all very, there are very intricate technical words we use in cricket. And nobody says that the technical words are the hurdles for people to enjoy cricket. They don't say that, right? Let's look at another area, cooking. If you are passionate about cooking and let's say you want to bake a cake, there are technical words which are used in cake making, cake baking. Whipping in cooking, particularly in baking cake, has a very, very different meaning than whipping in normal English. We also talk about cutting and folding. We talk about folding a mixture. What do you mean by fold a mixture? You can fold a paper. Yeah, you can fold a sheet. What do you mean for folding some semi-liquid stuff? What does it mean? Kneading. Kneading is different from folding. We use technical words in many places. They are not the main hurdle. I'm not saying that technical words are fine, there is nothing, no problem, but they are not the key problems. Okay, they are not the key problems in communicating science to public. As Einstein puts it, if you can't explain it simply, you don't understand it well enough. That's all. So the problem is not in technical words. Okay. Okay. Is the accuracy the issue? Science is very accurate. So that is why problems are there in communicating it to general public. Let's say, I'm sure we all in our elementary school would have studied in some class third or something like that, where the EVS starts. Okay. Earth goes around the sun. Yeah. Earth goes around the sun. Is it accurate or not? If you read a little bit more physics, you will know that planets don't go around the center of the sun. So if you have sun, if you have Jupiter, between them there is a point called as a barycenter or a common center of gravity. So the sun is going around this common center of gravity, and the Jupiter is going around this common center of gravity. So the barycenter depends on the two masses, where it will be located, right? So technically speaking, Jupiter is not going around sun. Yeah, but does it stop us from saying in third standard that Earth goes around the sun? No. If you learn more, if you learn modern physics, if we learn when we learn space-time curvature, we say completely a very radical stuff. Earth is not going around the sun. It is simply that because of the mass of the sun, the space-time curvature is curved near the sun. Earth is, after all, going in a straight line. That straight line gets curved into a near ellipse. Basically, space-time curvature. Earth is just following the space-time curvature. That's how you might describe when you are going to use relativity theory to describe the motion of the planet. But that doesn't stop you from explaining in high school the celestial mechanics, right? So accuracy is a matter of context. I'm not talking about something being wrong, okay? Accuracy is approximation. Approximation is different from error or something which is wrong, okay? Like if somebody says that the sun is going around Earth, it is wrong. It is false. But when you say Earth is going around the sun, it's an approximate truth. Maybe it's not absolutely true, right? It's approximately true. So there is a distinction, okay? So accuracy we need to keep in mind. We should not be telling wrong things. We should not be telling false things. That is absolutely correct. But accuracy is matter of context, okay? To the audience that you are talking about, it depends on that, okay? That's a so like Einstein says, everything should be made simple as possible, but not simpler. Sure, I'm not saying that technical words are not a problem at all, or the preciseness of science is not a challenge at all. But what I'm trying to point out is that these are not the key or vital problems. What are the vital problems? The vital problems are 5 characteristics of modern science. 5 features of modern science. They are the new reality domain, the counterintuitive nature of modern science, the constant shift between abstract description and a concrete description, and a shift from one to another. Constantly, we are like a pendulum going between abstract and concrete to abstract. Then many of the things that we talk in modern science are incongruous. And then modern science is seeped with organized skepticism. These are the 5 features which make modern science different, unfamiliar, strange to ordinary public. Let's explore each of this a bit more. Suppose if I ask you to describe your kitchen, utensils in the kitchen, you will call some of them as utensils, some of them as instruments. Okay. So your utensils might be made up of aluminium, it may be made up of ever silver, sometimes it may be even made up of pottery, right? Mud pot. You might be using pottery utensils for cooking. Some people are fancy, right? Yeah. But in science, when we classify this, we classify them as metals, non-metals. You know, the structure with which we classify in modern science is not the structure, same classificatory, let's say, bisects that we use in our everyday life, right? Yeah. So a mud pot in everyday life is a utensils. We don't see it as essentially different from another vessel made out of ever silver. Okay, because we focus on function. What are we using it for in our everyday life? But then when you are talking about science, you might be classifying them as metals, non-metals, and so on and so forth, right? So in modern science, we bring in new entities which are not in our everyday life parlance familiar. Okay. Similarly, in our modern science, we bring in new processes about which we are not conscious in our everyday life. Okay. We talk about, for example, the transport within cell, passive transport, active transport, the transport of glucose, transport of various proteins, so on and so forth, cell and the organism, the transport that takes place, right? Cell and the extracellular space, the transport that takes place. This is not something that we encounter consciously in our everyday life. Of course, every movement we live, every cell in our body is doing this activity, but we are not conscious about it. That's what I'm talking about. That's why I'm calling it as new reality domain, something that we are not familiar. Similarly, fossilization. I mean, is it something that you observe in your daily life? No. It's not even possible to observe it in your daily life because it takes thousands of years for fossils to occur, right? Same way, justification. When I say justification here, what I mean is that the kind of explanation that we give to reason out why something is happening in a one way. Like, for example, if kids claim the chair and drops a feather and a ball at the same time, obviously the ball will fall first, the feather will fall much later, right? Touch the ground. If you are going to answer it, why it is so, in your everyday life, you would say that, oh, feather is light, so it will take a longer time for it to come down. But then if you are going to give an explanation from physics, you are going to say that really both the ball and the feather has to touch the ground at the same time. That is what should have happened. But it did not happen because of the presence of air. Air, there is something called air resistance. That air resistance is more for a feather compared to a ball. So you bring in many other factors to give an explanation, give a justification of why something is happening in the way that we are observing. Okay. So it's a new reality domain. This constitutes new reality domain. This makes modern science and what we explain jarring from people's personal expectations. So the entities, processes, justification, new reality domain brings in many new features. If you look at counterintuitiveness, okay, I'm sure you are all physics students, so you know about the double slit experiment. Our intuitiveness will make us expect the particles, when you throw them through double slit, to hit the screen in two bands. But then what we get is infringement patterns, right? A pattern. which is not what we expect. So there is some counterintuitiveness to modern science in many things that we say in modern science. Okay. Evolution. Is it very easy to understand evolution? Let's look at something like a eye. There are so many components in the eye, right? And that so many components are so finely arranged so that the eye can function properly. And to imagine that this complex organical arrangement of an eye could have emerged through natural processes by random occurrences seems to be something not easily acceptable, right? Yeah. But we know, when you are talking about eye, we have evidence, we have data. Very clearly, we know that how eye evolved naturally without any hand of intelligence playing any role, right? You don't need any god. You don't need any other supernatural things to play a part in the evolution of eye. It evolves naturally. But that's not something that is very easy for us to stomach. Very, very counterintuitive, right? I mean, there was a philosopher called William Paley around 1850s. That's the same time as Darwin, remember? Okay, so he made a very famous statement that if you are walking in an uninhabited island and then your leg hits a rock, you will think that the rock was there always, or maybe the rock rolled from a nearby hillock. Okay, so you are not surprised by a presence of a rock on a seashore. Okay, it's not a big surprise. You can give an explanation which is easily understandable. But suppose if you find a watch, wristwatch, okay, can you say in the same way that the stone was there, the watch was also there forever? That was the kind of question that he was asking. In fact, he was challenging Darwin that how very organized forms, like if you are looking for from single cellular to multicellular, even in multicellular organs like eye, there are a lot of organization, right? Intricate organization, right? So those organization, how can it emerge on its own? So he was putting up a challenge. But today we know from 200 years of our research in evolution that even a very complex organ like eye evolves. But then for a person who is not very familiar with evolution and the mechanics of evolution, it looks very, very counterintuitive. It's very easy for us to fall for Paley's argument, right? Yeah, so counterintuitive. Then when you are talking about abstract and concrete, when you talk about physics, you say that a feather and a hammer should fall at the same time. Then you say that, oh, that is abstract. In concrete, we are talking about when in the presence of air, right? So basically, we are shifting from an abstract presentation to a concrete. I mean, sometimes people will call it as science in general to science in particular. Science in the general is your theories and laws and all that. Science in particular is in a particular context where so many other factors come into being. We move from one to another, abstract to concrete. So this creates some kind of a confusion, as if that we are talking with a double tongue. Okay, that's a kind of image that sometimes occurs. I told that modern science is incongruous in many ways. It's too abstract in physics, for example, too theoretical in mathematics, too remote in time, remote in place, prehistory, cosmology, too small, something that you cannot even, not only not see with your eye, it's even very difficult to imagine. Molecular biology. Sometimes it's inaccessible, like genetic therapy. Okay, so there is incongruousness to modern science, which also makes science strange It's not something your everyday experience. Lastly, when I talked about the 5 characters which are making science difficult to stomach for ordinary public, sometimes even to us, forget about ordinary public, is it's organized skepticism. Okay. So in the organized skepticism, we constantly ask why that should be true. Okay. When you get a scientific paper for review, the first thing that you start with is saying that this paper should be wrong. That's how you start. You don't start with understanding that this paper will be right when you are doing a review. It's not that we wish that author should be wrong. It's not that we wish that author should fail. But that is how the science brings in skepticism to ensure that what we claim as adequate evidence is closer to truth, that we achieve only by the fire of skepticism. Okay, that skepticism puts off people significantly. Okay, like people are worried when we say that, how do you know that it is true? So you mean to say that I'm lying? No, we are not talking about that you are lying. We as human beings can make mistake. We are frail, right? So the science wishes to avoid such mistakes. Sometimes we may be motivated by biases, unknown biases, ingrained biases. We want to avoid it. We want to be as objective as possible. So, which means skepticism is a very important feature of modern science, and that actually puts off a lot of people because they feel threatened. They feel that they are challenged. Okay. I explain in my view what are the key functional problems in communicating science to ordinary public, modern science. So how do we do it? Problem is one thing. They're all problems. Okay. So how do I handle the problem? How do I overcome the problem? That's 3 golden rules of science communication. We use 3 principles called as from known to unknown. That is, you start explaining from a known thing to the public and lead them to the unknown stuff, what they don't know. Again, you start from some simple thing and then build the complexity. Similarly, you start from explaining a particular and then build the general. Okay, so these are the 3 golden rules that we use in science communication. So there are various strategies, various tools that one can use in science communication. That is particularly making unfamiliar familiar. I told you that these 5 features, the 5 features of new reality, domain, counterintuitiveness, abstract, concrete, incongruous, organized skepticism. To an extent, we can use 4 strategies to address it, because they all make science unfamiliar. So some or other you want to make it familiar. One of the tool is analogy. Okay, so for example, if you want to explain how some simple fundamentals of genetics, the dogma of gene. Okay, you say that the DNA is like a cookbook. Okay, and in a cookbook, as there are chapters on South Indian cooking, Western cooking, Italian cooking, Punjabi dishes, same way the DNA has chromosomes. And within, let's say, South Indian cooking, there is a recipe for making tair vada, curd vada. Similarly, in the chromosome, there is something called as gene, which codes for making a particular protein. Right? So we are using analogy. right? So same way, from known to unknown, recipe books, so on, are something that we are familiar. From that, we are through analogy making known to unknown, right? Yeah. Sometimes we can also use metaphors, or sometimes it's called as imagistic expositions, right? So whenever we talk about immune system, we use the words like invader. The pathogens are invading our immune system cells, like macrophages or T cells, B cells, antibodies. They are as soldiers. Some are ordinary soldiers, some are border security forces, some are killer unit, some are special operation unit. Basically we are using a imagery of war, okay, to explain immunity as a war. I mean, many times we use this in other areas too. Like, for example, we talk about the constant Cold War between, let's say, prey and the predator. Okay, so the predator cultivates certain defenses, the prey creates something to overcome it. So there is a constant evolving Cold War between them, right? So these are all imagistic explanations, right? So this is also something we can use. We can also present some real life examples. When I say here illustration, I don't mean drawings. I mean real life examples. Okay, like if you're talking about weightlessness, okay, why, for example, people float in spacecraft going around the Earth, like International Space Station. Why people float in it? You can talk about weightlessness, and then you can link it to people's experience. So if you had gone in a merry-go-round, when the merry-go-round is just about to reach the top and then just about to come below, okay, when it's going around, when it has reached the top point and then it's going to come down, that instant, we suddenly feel that we are as if we are floating, right? That's the experience of weightlessness, right, in our everyday life. I mean, sometimes in a lift, I mean, if it is a very tall building and then the lift is really fast, when the lift starts, that instant, we feel as if we are floating inside the lift, right? That feeling is what is the experience of weightlessness. I mean, you can give from real life example. Then you can also do use something called as thought experiments. Okay, science, lot of thought experiments. Einstein used a lot of thought experiments in Schrodinger cat, for example, is a thought experiment that we use in quantum mechanics. Okay, so same way, thought experiments can also be used to communicate some intricate scientific ideas to common public. One of the best example is Hilbert Hotel. I am not going to explain what it is. You can Google it. Please read it up. Hilbert Hotel is a thought experiment that's used by maths popularizers, maths educators to explain concepts of infinity to ordinary public. Okay, so that's a thought experiment. Okay, so let me go further. So when we encounter something which is strange, okay, unfamiliar, what do we feel? Suppose when you go to some really new place that you have never been, like maybe some South Asian country, maybe Korea, okay, and then the food is on the table. None of them you have seen earlier. Of course, now Korean food is becoming popular and we are all seeing it. That's a different issue. I'm just saying, for example, or maybe some Africa and then some African food is on the table, right? What do you feel? Same way, suppose you go to a new city, new place where you've never been. Maybe you don't even know the local language, okay? And it's dark, gray. What do you feel? Okay, when you land there, when you encounter something unfamiliar like this, what we feel is strange. We feel very strange, right? That's exactly what ordinary people also feel when they encounter science with this characteristic. Okay, unfamiliarity. Unfamiliarity is one of the key cornerstones. Okay, so strangeness. So when you feel strange, you feel bit of threatened, you feel bit of risk, right? So how do you respond to risk? There have been studies which tells us that there are 4 ways in which we react to risk, or rather we look at risk in 4 ways. So I can classify this in a XY coordinate. Like I can look at the knowledge about the impact. What is my knowledge about the impact? When it is less, when it is more. That is when I am unsure about what will be the impact, when I am sure about what is the impact, less and more. Knowledge about the occurrence. How much I am sure that such an event will occur or not occur. Okay. So when I am less sure, when I am absolutely sure. So if I can make this, I can get 4 quadrants. Okay. So 4 quadrants of how we respond to risk. Right. So now let's look at the first quadrant. When I'm sure about how much the occurrence is going to occur, and I'm also sure about what is going to be the impact. Right? So it's a known thing that we are certain. But then there can also be exactly opposite. I know very little about the occurrence. I also have very little idea about the impact. So it's an unknown. We don't know what we don't know. It's also not that we don't know. We also don't know what we don't know. Okay, it's a slightly more tricky situation. Then there are 2 other quadrants where our knowledge about the occurrence is substantial, but the impact is not so much. So then we know if they are all known unknowns. That we know that there are things we cannot predict. Okay, so there are some unpredictable stuff. It's there. We know it. Then there are things where we know more about the impact. We are certain about the impact, but we don't know whether that event will occur or not. These are unknown knowns. Others know, but you don't know. Okay, so that is the situation. So these are all the 4 simplified, let's say, quadrant of response to risk. Okay, you can look at it in this fashion. So if you look at how public respond to each of this situation, when it is known, that is that we are certain of what is going to happen. Okay, we are occurrence and also impact. We are not having any big doubts. Okay, what we may have is perhaps disagreement, but certainly not fear or anxiety. Okay, so the emotion is not fear or anxiety, maybe disagreement. So a question like, say, for example, should a poor country like India engage in research like India-based neutrino observatory? Okay, that's a known. It does not come from some fear or anxiety. It's basically a disagreement. Okay, so why not spend this money on some useful research? When people say this, that's not fear or anxiety. So when public response, when I say public, I mean a section of public, not everyone. Not everyone responds in the same way. Okay, if some people are responding like this, what do we do? How do we react? When it is a question of disagreement, that is when it is about the known knowns. Okay, so it's important for us to explain why fundamental science is important. If during 1820s, if J.J. Thomson had not worked on electron, you won't have electronics today. At the time when he was working on electron, nobody had any idea of what that study will lead to, what kind of useful product or technology it will bring in, right? So fundamental science is important. If we have not studied positron, there is not going to be a PET scan, right? So who knows by studying neutrino what we will bring in, right? So one need to explain calmly and coolly why fundamental science is necessary. Second, we also need to show that the so-called expenditure towards science is actually investment. It's not expenditure. Okay. And then you can compare. If you look at the total money spent in Tamil Nadu alone, I'm not talking about all India. I'm talking about Tamil Nadu alone. And on Diwali, I don't, of course, Diwali taskmask is closed. I'm talking about the day before Diwali. Okay. Diwali is a dry day, right? The day before Diwali. The money spent on taskmask is about 4,000 crores. Okay. So when money spent on INO project for 10 years is 1,500 crores. So compared to this expenditure, where are we? Is it really that big amount? Okay. These are all things that one can present to make reason with public, larger public, including people who have this kind of a view. So that is one. Now let's go to a second area where it is a known unknown. That is, we know, but then we cannot predict very clearly. Here again, what happens is not fear or anxiety, but worry. Okay. Questions like, say, for example, noise during the construction, dust during the construction, free movement, or will the explosive damage the dam? You know, these are all some of the questions which will fall within this category. So how do you address the worry? Explain what measures are being proposed to address them. Explain that the shock wave generated when they travel distance, the effective strength will go down by 1 by r square. Okay. So if the shock wave is going to travel till 30 kilometers, it's not going to be even perceptible. It's not even measurable. Even 500 meters, the shock wave will be something like a clapping of a hand, right? So explain that part. And then also show that how various tunnels have been built in the same region. Okay. And that has not caused any damage. So this is why, I mean, we try to respond to those kinds of worries. Okay. Then there is a next quadrant, which is unknown knowns. Others know it, but you don't know it. Meaning that the people who are talking about it don't know it, but we know it. Or larger scientific community know it. This brings in anxiety. Okay, because you don't know, it brings in anxiety. What kind? Will there be land acquisition? Will people be evacuated for 1 kilometer around this region? Okay, what is the amount of water that will be consumed by this project? Will it cause water stress in my region? Right? These are all kinds of questions that comes in within this framework. So the way you explain is, sorry, I think, okay, so when you have this, my slides are a mistake. Okay, so I'll go this. So you explain the facts that not even a single inch of land will be required. There is already a water tank constructed in that area. So that is the amount of water that will be required. So if you go and look at that water tank is like a water tank of a normal housing complex. That's it. Okay, so it's not going to cause any water stress in that region. It's not substantial. Okay, so one can give these facts and figures and alleviate the anxiety. Okay, you can give a clear assurance. Nobody's land is going to be taken away. Nobody is going to be evicted because of this project and so on. Right. So there is no need for unnecessary anxiety. Okay. So that's the unknown unknowns are the most complicated stuff. Okay. So this creates fear and dread. Okay. Questions like world's largest magnet, what will be the impact? Okay, one of the claim that was made was that the neutrinos will be attracted by the world's largest magnet, and when there is a power cut, and usually power cut do happen, these neutrinos will bounce back, damaging 100 kilometers around. I mean, completely ludicrous stuff. So one need to explain science. One need to say that the neutrinos are chargeless particle, so cannot be attracted by magnet, And the world's largest magnet does not mean it's world's powerful magnet. It only means in size. Okay. In terms of strength, even a CT scan has much CT scan instrument has much strong magnet compared to this, right? Yeah, good communication will help. So making unfamiliar familiar will help in this particular case to address fear and dread coming out of this unknowns. Okay, but then these are not the only 4 challenges or problems that we see around us. Okay, if there are only 4, it's easy to handle. But then there are more. One of them, when I talk about the addition to this 4, is social movement. Social movement question the legal, ethical, political, and social justice question. Okay, so one of the questions that a large number of people ask, many of us also ask, okay, is why there is a lack of diversity in Indian science. Of course, international science too, but it is very stark in India. Why? What do we do about it? Okay, so it's a challenge. There may be people who may ask that whether all the legal requirements that is needed for a project to be executed are met. Okay, so the questions from social movements are not really the problems. Okay, they are not the hurdles for any good project to take off the ground. They are not the problems. They are not the hurdles. They are needed in a society like us if we want a good democracy. Ultimately, whatever that we do need to benefit people, right? So for benefiting people, functioning democracy is needed. In a functioning democracy, social movements and their roles like social justice questions are important. We cannot deny that. Okay, so one need not fear or one need not worry about social movements. If they are asking, it's a good time for us to reflect on it. That's all. Okay, so that's not a challenge. But real challenges come from another area which is recently emerging and becoming stronger in India. This is called industry ideology propaganda. Sometimes it's also called as post-truth, which is basically willful ignorance. It's not just ignorance, that is you don't know. It's willful ignorance. That is you think that I don't need to know, or you think that I know everything that is needed to know. Okay, so that kind of this industry and ideology-led propaganda leads to aversion, animosity. The emotions of aversion and animosity. It pits, within quotes, people and scientists as 2 enemy camps. Okay, this is where we need to be careful. This is what is the important challenge in contemporary times, or rather important additional challenge in the contemporary times. So questions like, for example, natural neutrino and artificial neutrino, that it's a Fermilab project with the aim to make the bomb. Okay, so these are all some of the claims that goes around in the ideology-led propaganda. Okay, so in this ideology-led propaganda, sometimes they are all from junk science. Corporates create junk science. We know that, for example, tobacco industry kept on lying, kept on creating research which doubted. In climate change, the fossil fuel industry is creating so-called junk science to create doubts. Okay, sometimes it is about fake news, post-truth. Recently in India, there has been this claim that cow is the only animal which breathes in oxygen and breathes out oxygen. All of us do, because we take about 21% oxygen. All of them is not absorbed by our body, so a substantial amount comes out. But if we don't mean that, but really that like a tree, cow is producing oxygen in its body process, bullshit. Yeah, or cow shit. Yeah, so but that kind of false claims are around, right? There are also claims from deep ecology. This deep ecology says that humans are virus, like this is a kind of statement which was going around during lockdown, right? Earth is recovering, air pollution is slowing down. They are all during lockdown, right? Water pollution is clearing up. Natural wildlife is returning home. That is, peacocks are dancing on the road. Dolphins are seen on the riverways, blah, blah, blah. So coronavirus is Earth's vaccine. We are the virus. This is a kind of statement. So basically, the claim seems to be that humans are the enemies of nature, and then we should return back to nature. But is it really true? We need to ask this question. See, if you look at the global pyramid of wealth, about 1.1% of global people, 1.1%, okay, 1.1, you hear me clearly, they own 45% of global wealth in 2020, but only 1.1. If you take 11.1%, they owned additionally another 39%. So which means about 12% of world population owned close to about 84%, 85% of world wealth. 85% with just 12%. Then if you look at the middle, 32% owned about 13%. If you look at the bottom, 55%, they own just 1.3% of the world wealth. Are we going to say that all these people, without any distinction, are equally responsible for the environmental pollution that we see today? So are they all virus? Well, there is something really wrong here, right? So if you look at India, so richest 1% in India own 51%. Then the next 4% own 17%. If you look at the poorest 60% in India, they share just 4.7% of India's wealth. So can we put the blame on all of them equally? There is something problem with this deep ecology, putting men or human as the enemy of nature. Really not. Okay, but then that's how these activists are talking today. There is also a new trend called science denial, where you use fake expert, logical fallacies, impossible expectation, cherry picking, conspiracy theories, all this combined to make science denial. Vaccines don't work. Vaccines create a corona disease, COVID disease. Things of this kind we see around, right? So science denial, right? So what do we do with this new challenge? Challenge which comes from ideology, industry, propaganda. Ideology, industry, propaganda. Okay. So one is effectively way to challenge, that is debunking. So in this debunking, you are presenting facts. Okay, you are presenting facts which will burst the myth. Okay. Second, you are pointing out fallacies in the argument. Okay. And what are the misconceptions which are there in the argument. So by exposing this, that one can challenge some of the industry propaganda, ideology propaganda based challenges, science denial challenges that we are seeing around. Okay. So when you look at a question like, for example, Fermi Lab, okay, so that India-based neutrino observatory is a handiwork of Fermi Lab research project whose aim is to develop a neutrino bomb. That's what is the claim. Just look at Fermi Lab. Just look at the project Dune. It's a multinational project, which means in addition to USA, other countries are involved. India is involved in that Fermi Lab project, of course. But along with India, Pakistan is involved. So do we mean to say that this neutrino bomb project is jointly done by America, India, and Pakistan? Well, look at the list. Iran is involved. So do we really mean to say that America and Iran are jointly developing neutrino bomb in Fermi Lab? Stupidity, right? So complete falsity, right? This we need to bring in. Okay, when we are going to challenge these kinds of argument, These kind of points we need to bring in. So essentially, from known to unknown, simple to complex, particular to general, this will help us in addressing some of the challenges that we see from detrackers, science denial category people that are there. In addition, earlier I told you about 4 ways in which people respond because of their knowledge and ignorance matrix. Okay, so that's everywhere for everything. It's not only for projects about related to science. That's about everything. So combinedly, we need to look at the challenges before us, and then we need to address it accordingly. Okay, so this is what I would like to share. There are some interesting comments in the question box. Of course, there is a FAQ question that will take it up next one. Surjit has really, sorry, Sudhit Raj has made a very good point that we are familiar with the cricket, and that's why we are not, distracted by the technical terms, perhaps. But I gave you another example, right? Cooking. There are many places, even in economy, we say balance of payment crisis, inflation. We use technical terms. That itself is not something that makes it easy or difficult. Okay. Okay, I feel good when I share my knowledge with others and when the science reaches common people and helps making life better. How one BSc physics student and an aspiring researcher can become a science communicator? This is a question from Krishna. Welcome. That's excellent. Basically, you become a science communicator by actually communicating science. You learn swimming by jumping into the water, right? So don't worry. Yeah. So some point that I made today, keep in mind. Maybe read up a few more, but then keep doing. So when you are working with people, you yourself will know whether things work or not. Okay. So that will help us. We do need a lot of people to talk about science in India for various reasons. Okay. So welcome and join our club. I think I'll stop here. I think my 1 hour time is also over. So if there are any more questions or other comments, I can take it up. Thank you. Okay, so there is another question that how can we speak against politicians who have a lot of support and spread false propaganda? Well, I mean, it all depends. Okay, how you want to go. Okay, there is a very famous drama on Galileo. Okay, written by a German playwright called Bertolt Brecht. Okay, so in that drama, he points out that Galileo does protest when people say something wrong, but at the same time, when Galileo is pressurized by powerful people, Galileo says that I'm not going to lose my life, but truth is truth, right? And generally, nobody is alone, right? So when you are going to speak, it's not you going to speak, we going to speak, right? So it's not never like you are going to be alone in the ground. Okay, we are going to speak, so that's fine. So there is one group which speaks, so another group can speak, and we don't need to personalize it. No, see, only by personalizing, we'll be inviting certain kind of issues. Without personalizing, we can talk. We do talk. Okay, we do talk about it. That's fine. TN's current ruling party, it's about not about only current ruling party. There is a consistent effort by certain groups in Tamil Nadu. Okay, but then you have to also see it in the larger framework of the science deniers growing up. Okay, so it's not about one political party or one individual. It's a larger thing that is happening. So we all together can make a change. We did make a change when we had a good dialogue. We were able to make at least few people rethink. Okay, so we need to do that. We can't be silent. Yeah, fine. Thank you.
Hello?
Yeah.
Yeah, can you hear me?
Yeah.
Yeah, okay. Thanks so much. Actually, can you see? I think you have lots and lots of questions.
Yeah.
Which are, of course, expected. Do you want me to read through, or do you have chat and you can answer some of those?
Actually, before TVV starts, I want to add one slide to what TVV was saying. Can I? If you allow me to, can you please allow me to share screen?
Yeah,
please.
So, Raghav Krishna, you're a BSc student, is it? Where do you study?
Raghav Krishna, where do you study?
Yeah, Indu.
Oh, IMSc. Okay, nice. I
Indu,
like your spirit. I like your spirit. Okay. Yeah. So I like to show this. It's something that I've shared with many students. This is a Gaussian distribution. Everybody knows it's a Gaussian distribution. It says so at the bottom. So if you add up 34 and 34, I get nearly 70%, right? That is a 1 sigma distribution. So what I want to say is that 70% of the people normally don't care either way. This is in the middle, that 1 sigma distribution, okay? So you can see that of the remaining 30%, 15% are strongly for and 15% are strongly against something. It's always true, okay? That's what the Gaussian distribution means. It's a normal distribution, okay? So I think that the people that, especially that 0.02% who are against the project, right? I think that rebellion is not required in order to persuade that 0.02%. You actually need to talk to the 70% very large numbers and convince them about your project. And very often they are reasonable people. They will be willing to listen. And you have to just move them a little towards your side so that the mean itself moves a little, okay? And just, you can see that 70% is a very, very large number. So even if a small fraction of that moves, you can actually change public opinion, okay? So you will never be able to change the opinion of this 15 or 10%, okay? That is kind of cast in stone. So, but there is still a lot of leeway in a democracy. There is a huge group that is waiting. Of course, if the government who gives you your clearances are sitting in this 0.02, that is in this 2%, then you have a tough job. But even then, within that 2%, there will be, people who will be willing to listen to you, and we have to actually find those. So I'm one of those optimistic people. I think we will never say that it can't be done. But it's very important to understand this, that whenever you see on TV, for example, public opinion, it is due to very small percentage of very vocal people. Somebody is talking, can you please mute? So it is due to this very small percentage of people who are extremely vocal for or against. The major part of the public actually don't care. And in this sense, I think that there is a lot of leeway. Even without revolutions, I think you can get things done. And one last point I want to make is what Venkateswaran says is something very important in today's modern context. The world has become so scientific and so technical that the common man is really left behind, doesn't know what is true and what is not. And in some sense, you people who are physicists, who are actually science students, who can actually read and find out and actually convey the truth, are a very, very important component of today's society. And I think Dr. Venkateswaran showed in a very, very nice way how you can play a very, very important role in the shape of society to come. Because it's not just INO. I think there are many, many things today. If you just read the papers, you will list your own top 5. I don't need to do it for you. And you can see that there's a lot of absence of clarity and no scientific or technical person who is speaking on those issues. Just a lot of opinions and comments. This becomes very important to actually counter in today's world. So those are the 2 points I had to make. Thank you.
So, can you TVP?
Yeah.
Okay. Will you be able to take some questions? Some more questions?
Sure. Yes, sir.
Okay. Just give me a second. By the time, if you can just read first few questions on the chat, I will get back to you.
These questions I have actually answered.
Okay, just give me
the chat one. I think I have actually looked at.
Okay. Okay. So are there any more questions? Hello?
Yeah, that's I think fine. We can maybe move to the next session. Yeah.
Okay. 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 Just one. I have slight challenge about the Wi-Fi connection, so that is why I'm taking a little more time. Yeah. Okay. There is one question says you mentioned joining you for science communication. How can I do that? Hello? TV, can you hear me?
Yes.
It says something about science communication.
Okay. There are 2-3 ways you can look at it. One is there are popular science movements in many parts of the country. Like if you're talking about Tamil Nadu, there is a Tamil Nadu Science Forum. We are all part of it. So you are most welcome to join it. That is number one. Second is if you want to have some more professional training in science communication, keep watching the website of Vigyan Prasar. Okay, Vigyan Prasar, vigyanprasar.gov.in. We will be offering some science communication courses. Soon we are going to offer one in November along with NCL, National Chemical Laboratory. The advertisement will be available in their website also. So that's a week-long course. So you can also join some of these online courses to sharpen your professional skills if you are interested in that way. Okay, so third is actually do some science communication. I mean, after all, you would find that it makes you, I mean, more sharper. I mean, when you want to tell a larger public.
Yeah, sorry, please go ahead.
Somebody... Yeah. So these are all the stuff. And in the Indumati has also shared, for example, there is going to be a popular science lecture in part of the TNSF activity. So you can also contact Dr. Indumati for joining the Tamil Nadu Science Forum and things like that. Okay, so that's something that you can look at. Yeah.
Also, there is one question about your slide on cow inhales and exhales oxygen. So he query like, I want to know who did this statement really.
Okay, I mean about the cow, there are
holy cow, I mean, come on.
I mean, a lot of people have written about it, so you can just Google it, and you will find quite a lot of people have written about this stupid claim. Okay, so yeah.
Okay. Okay, I think I don't see any more. There are nice comments, but
so okay,
no
if you really want to know Satya, this person is Rekha Arya. This is the Uttarakhand Animal Husbandry Minister, who said that cow is the only animal that inhales and exhales oxygen.
Okay. That is the answer. Okay.
Yeah. It was, I mean, this has been going on for the last 2-3 years actually. So.
Okay. Okay.
Yeah. I can see that. Yeah, TVV. I can see that there is some noise at your place. Yeah.
Okay.
So I think that now that TVV has talked about it, I think all of you can realize that there is a lot of this stuff going on in the press. There is one thing to be proud of. Our, India has a very long history. It's a very old civilization, very ancient culture. All this is definitely true, but still facts are facts. I think science is science, and anything that contradicts science, we have to raise our voices against. So this is something that we should never hesitate about. Some things are extremely obvious to some of us, and if people are confused, I think if you know the facts, you should actually debunk the myths, because I think social media is one of the biggest spreaders of myths. And a lot of these myths arise because somebody believes that science can do everything. That's true. When I was young, you could not talk on the telephone without a wire connected to it. But now everyone walks around with a mobile which has, no wires attached to it. How do you even receive and send anything? So people believe that science can do anything. Okay. So it becomes very difficult to start telling what is possible and what is not possible. And I said this will only become more complicated as we go on, because technology has gone at such a pace that it's incredible, right? You just think about it. I'm talking to you, my hands are free. I'm just speaking into my computer, and all of you are listening to me, and you're all, across all of India, maybe hundreds, thousands of kilometers away. And if this is not a miracle, what is, right? But this miracle of science is something that we should be able to explain. We should be able to make people understand and appreciate, and use for the benefit of, distributing and disseminating correct scientific information. That is, I think, the job of a science communicator. And I think TVV had difficulty speaking. Both of us, Venkateswaran and I, are members of Tamil Nadu Science Forum. Huge numbers of us are members of Tamil Nadu Science Forum. I have been part of it for more than 30 years now. And a big mandate of Tamil Nadu Science Forum is to do science popularization, is to tell people what science means and how it affects the common man, and how it is to be used for the benefit of society. That is something that is very important. And these lectures, which are held every month, as I said, this is the chance now that COVID is on. They're all online. Earlier, they used to be only in lecture halls across Chennai. So those of you who are not in Chennai can also try and register. I think there is a limit on the number of people of about 450 or something. So you can please still register, and those who are interested, once you register, you will get mail subsequently telling you about the next program. Okay, so that will be a continuity for you. You can listen to all these lectures. They will also be on YouTube. So if you can't register, you can also listen to them on YouTube.
Okay. So Hindu, then now that I don't see any more specific questions to TVV, so let us formally thank Dr. T. Venkateswaran for his very nice and thought-provoking talk, and also which of course brought up a lot of discussion. And in the discussion, there are more points that have been kind of discussed. So it's very nice. And as usual, TVV, thank you very much. Always your trademark lectures, which will bring out more than what was intended in some. So are you going to be here for a while, or TVV?
No, actually, nowadays I have evening classes, so I have to run. Sorry.
Okay, no problem. Yeah. Thank you. Because now this will naturally go into the last session, which is in some way more of an interactive session with all the faculties. But we do understand your time schedule. So thank you once again. We of course
thanks TVV.
Thanks everyone. We'll be in touch. Okay, see you. Thank you.
Yeah, bye.
Yeah, you could see his email address, so everyone can write to him.
Yeah, I'm putting it in my.
Yeah, his name is there. TVV123@gmail.com.
Yeah, so please. Okay,
thanks a lot.
Thank you.
Bye.
Thank you. Thank you. So we have. Okay, so now we'll get to the last session of this particular leg of the outreach, and in fact, it is also really the last session of the entire outreach initiative, which has started on August 26th and going on till today. Let me see. I will want to bring more faculties if I can. If anybody can locate, please let me know.
Satya, maybe you should just give everybody a five-minute break so that they can come back in 5 minutes and then start. And in the meanwhile, you can,
Yeah, but 5 minutes will be too short anyway.
Okay,
really,
10 minutes then. Okay.
Really, do you want to do it? Because this is just one session. Let us finish it, no? I feel.
Okay, I mean, if the students are okay with it, I'm okay with it.
Yeah, this is okay. I don't. Do you, Indu or Amal? Do you see any of our faculties other than you two?
Let me see. So Subhabati will not be coming. I think she is.
Okay. And Murthy also is not coming.
Okay, fine. Okay.
Okay. I mean, I'm sure if Govindo and others join, please alert me and I'll pin them to the screen. But let us start in the sense. So as we talked this morning, okay, this particular session, interactions with participants, is more, of course, you have been interacting with the faculties all the time during their lectures. That is very nice.
So Vivek is there, by the way, okay?
Oh, okay, he just came in. Then you ask many technical questions related to the topic, and also some of them are actually related to your career and many things. So, but this is one, again, I would say last chance where you can freely talk to all the faculties about any question that you have in your mind. Okay, so we have 3 faculties who taught you in this program. So please feel free to start in asking your questions. You can unmute yourself and also ask questions as well. Okay. Wait, I'm not able to see. You said Professor Datar is there?
Yeah. I saw him at the bottom.
Yes, I'm here.
There he is.
Yeah.
Because you are not in alphabetical.
No, because those who have their microphones on are all in the top, right?
Now I can.
You should look for him in the top, not at the bottom. Yeah.
Thank you so much. I was about. Yeah, you are. Sir, you can also open. I mean, in case Indu and Professor Datar, you can also put on. Yeah, camera. Sure. Your camera also.
Yeah.
Indu, you want to keep your camera on?
Sure. I can.
Perfect. Okay. So now so now questions are coming up. If Indu, maybe you can try to locally coordinate.
Yeah, sure, I can do that. Yeah, Satya, you have done some yeoman service.
So we'll
take a break. We will organize. Yeah.
No, I'm here.
No, I know that. Yeah, but yeah. So okay. So the first question: will chemistry students have job opportunities in neutrino research? I asked Vivek to address this question.
Yes. I mean, when the project comes up, certainly. When the work on the project starts, but even before that, you can. I mean, job is something I don't know. I can't comment on that, but certainly you can do projects. You can join any of the institutions to do your PhD work. There are, these things have been going on for many years at the various institutions. DA institutions, of course, like Ag Science, like TIFR, like HRI. By the way, BRC also has a program which involves HBNI. So you can apply for a PhD in physics through HBNI and through BRC. Okay, so that's also an option. And BRC is certainly part of the INO project. Okay, so job opportunities, I think, one can have temporary jobs in this project. They are called project posts, both in this scientific posts as well as technical posts. So I don't know whether that answers your question.
So Vivek, maybe one aspect of question is, what can chemistry students do to use their knowledge of chemistry or interest in chemistry for INO? And one thing I thought was maybe gas mixtures. Isn't that a chemist domain?
Yes, that is.
You can explain that maybe.
So when as I said, when the project really starts, then of course the project authorities will ask for permanent staff, and at that time we will be recruiting a fairly large number of permanent staff. Till that time, it will be in the area of temporary positions, project positions.
The question actually doesn't ask about INO positions. It says, will there opportunity neutrino?
Let me look at the question.
What's the job opportunities in? No. Previous one. Will chemistry students have job opportunities in?
Will chemistry students have job opportunities?
For example, the deuterated this thing, right? It's also chemistry, right?
That's right. But these things, of course, have yet to come. It's true that they will come up one day, but right now they are. I mean, you can't say that you will recruit people for chemistry. But I think project posts, perhaps there might be a scope, because once the engineering module starts coming up, I think you will. there will be a requirement for chemical engineers, chemists, and so on.
Okay. Now maybe Amol can add to this answer.
Yeah. So I'll actually answer the question. I think the question can be taken in a broader sense. You see, the neutrino research, a large part of it actually is chemistry research. The first person who got Nobel Prize for looking at solar neutrinos was a chemist. This is a chemistry experiment, so nuclear chemistry experiment. So, for example, the neutrinos from the sun were detected by Davis, right? And that experiment is basically a chemistry experiment. So, what is that? What is needed for that? What is needed is it was I think chlorine going to maybe argon.
Chlorine 37 to argon 37.
Argon. This was the reaction. Okay. Now at that point of time, the idea was for 1 month or something of that kind, you expose the detector to neutrinos from the sun. After 1 month, you take out these few kilotons of material that you had, and you filter out argon atoms which have been formed. Now in 1 month, number of argon atoms that will be formed there would be of the order of, I don't know, maybe 50. Okay?
10 or 15 or something.
Maybe 15 or
It's one every 2 days.
Yes. And
600 tons.
Then you need chemists to be able to separate these argon atoms from this whole big detector. And this uses chemistry purification method, which are known only to chemists. So in that sense, I think in many of the experiments in neutrinos that have gone on through the years, the contribution of chemists has been important. So in fact, a large part of these experiments are called as radiochemical experiments. Okay? They use ones that use gallium, for example, or ones that use, as I said, chlorine. There's also a possibility that people have tried now, which is to add a salt called as gadolinium salt inside big water Cherenkov detectors, so that you can detect neutrons very well. So all these means of purifying detectors and trying to make use of chemical properties of elements is a domain of chemistry. So overall, expertise in chemistry is, I think, quite crucial part of many neutrino detectors. In INO detector itself, perhaps chemistry is not very useful in making iron because iron properties are known. But remember, we are gas mixture. So the gas mixture consists of a few gases, and of course, how the interaction of them helps us in getting a better signal is again something that somebody from chemistry can work on.
Yeah, maybe I should add to what Amol is saying. Certainly, the gas that is being used presently is going to be replaced in all RPCs in future from the R134A, which is actually a greenhouse gas, to a gas which is not so much of a greenhouse gas, which means that already there are gases that are being looked at which have the same greenhouse effect as carbon dioxide. And in any case, this will not leak out very much. So if a little bit of carbon dioxide goes out, leaks out, that's okay. Because the present gas is about 1400 times as bad as carbon dioxide as far as greenhouse effect is concerned. Of course, this gas, the present gas, doesn't have any adverse effect on the ozone layer. That's why it is being used in refrigerants. In your refrigerator, for instance, you have this R134A. Earlier generation has had things which are bad for the ozone, which contain basically chlorine compounds.
Okay, so I think that question has been answered fully. I also added some things in the chat box. So
let me just add 10 seconds of my answer.
Please do.
So there were actual cases of, let us say integrated MSc students in chemistry from CEBS coming and working in INO. I myself had a couple of students from chemistry background who came and did a work on so-called residual gas analysis of what Professor Datar and Amol mentioned. They actually worked on kind of quantifying the contaminants in the gas. Some of you must remember Professor Datar's talk, where when the gas that you flow through the detector, which is so-called active detection medium in which the ionization happens, is not something you consume. Gas is actually not consumed. Gas is just a medium which flows from input to output of the gas ports. But unfortunately, because you have many joints and lots of pipes, and so there would be always some contaminations that happen from, let us say, in the surrounding atmosphere or by other means. So it is very important that you quantify these radicals, because anything that happens beyond the designated gas mixture will bring down the efficiency, performance of the detector for the neutrino experiment. So it is very important that you monitor these contaminants online as the gas system works. Okay, so therefore there are these techniques called residual gas analyzer, which is actually in some ways a mass spectroscopy, and also what we have so-called gas chromatography, which also gives you online what are the mixtures of these three gases that you originally intended for the optimal performance. Are you able to maintain these performances? This entire field is actually chemistry. Okay, and then we design these online systems to be able to monitor 24/7. So therefore, as I think I'm just I said that there are such examples. That was my main idea to show. But yes, there is even for internships, there are some opportunities for people with chemistry background. Thank you.
Yeah, very nice clarification, Satya. Thank you. I'm addressing Pushparaj Ghatke's question on what's the method to distinguish different neutrinos, like solar neutrinos, atmospheric neutrinos, or those produced thousands of years ago. So I have this graph. It's basically the energy, okay? Different neutrinos with different energies interact differently with different detectors. So you can see that the solar neutrinos, so this is an electron volts. By now you are familiar. A mass of an electron is 500,000 electron volts. That is sitting over here. This is 10 power 6, which is 1 million electron volts. And you can see that the solar neutrino comes somewhere here. Supernova is not very far away. Atmospheric neutrinos come at 10 power 9 to 10 power 10, which is giga electron volts. And reactor solar are all very, very similar to each other. Terrestrial are even lower energy than reactor ends at 8 million electron volts. Terrestrial is about 1 million electron volt. And the neutrinos that started from the Big Bang, which were produced not thousands but billions, 13.7 billion years ago, are such low energies, milli electron volt energies, that they have not yet been detected. It has simply been assumed that they exist. Okay, so you can see that different detectors are sensitive to different energies of neutrinos. For example, the ICAL detector will not be sensitive to MEV solar neutrinos, but only to GeV atmospheric neutrinos. And this is essentially a major way in which you can distinguish these neutrinos. Of course, you can also distinguish them once you detect them. You know the fluxes of them. For example, you know the pattern of neutrinos that are emitted in the chain reaction, say in decay chains of plutonium or thorium. And so from there, you can also try to see whether you've got it right. So there is a kind of a cross-check to this.
May I add to this, Indu?
Yeah, please do. Should I keep the thing in front?
Sorry?
Should I keep that graph in front?
Oh, no, that's not needed. So, so one way of distinguishing neutrino sources is, of course, as Professor Indumati said, looking at the energies. The second way is looking at where they are coming from. So, for example, if you look at neutrinos, neutrinos coming from the sun, if your detector can tell you where they are coming from, then you can have some idea. So, for example, the solar neutrinos come from the sun. And if you have a detector such that you approximately know where the neutrinos are coming from, you can actually know that they're coming from the sun. This experiment, Super Kamiokande, that you must have heard about, actually looked at the sun for almost 15 years. And they have a photo of the sun taken in neutrinos, not in light. Okay, so if you find it, we can of course show it to you. But direction is important. A few years ago, at the end of 2017 also, an object called as blazar went up in the sky. Now, blazars give out lots of particles, including neutrinos. One of those neutrinos actually was detected in the detector called as IceCube, which is at the South Pole, as you may have heard about. And the accuracy in the direction of this neutrino was so fine that you could actually point back at where the blazar was. And indeed, because of this, other detectors like X-ray detectors, gamma ray detectors, optical detectors could look in that direction and then after some time actually observe that blazar. So indeed, with neutrinos, sometimes even direction tells you where it is coming from.
So Amol, 2 points. One is I put up that slide, and the other is maybe you should explain that very curious statement was of after some time they could see the blazar. I think it will be very interesting for the students.
Yeah. So this is quite interesting. Okay. So sometimes what happens is something great happens in astrophysics. Okay, a supernova blows up, or a blazar happens, or something great happens. Now, see, things often happen in regions where there's a lot of material. Okay, and you know, if there's a lot of material, then that material cannot allow light to pass through. Okay? So imagine the case of a supernova exploding, for example. Okay, so what happens in the supernova exploding? Lots of things are happening because of which explosion starts happening. However, until the star explodes completely, light cannot come out of this. Okay. On the other hand, neutrinos can come out because neutrinos are very weakly interacting, so they are not stopped by the star. Now imagine that there is a star which is going to go supernova. Okay. Now it takes about 1 day for the explosion to happen. So the explosion starts from the inside, and the shock wave travels outside, and after about 1 day, the star explodes. Now, neutrinos start coming as soon as explosion starts, okay, because lots of them are produced inside that. Whereas light starts coming only when the star actually explodes. What does that mean? That means that neutrinos started about 1 day before the light starts. So you have got a head start. Okay? And this means that if you see neutrinos on Earth, then you know that from that direction, sometime in future, other particles will come. Okay? If it's a supernova, it will happen in 1 day. If it's a blazar, it will happen or keep on happening for next few months. So neutrinos also often work as early signals of what's happening in the sky. So if you have a telescope, optical telescope, and you want to look at a supernova, okay, what you will say is that, okay, so today I know that a neutrino has come from supernova. So tomorrow in the sky I will see a supernova. So of course, first thing you will do is you will not sleep. You go to your telescope and you point it in the direction that has been indicated. So now you can see the supernova from the time 0. You know it's going to happen now. You can actually see it's like the IPL match is starting today at 8 o'clock. No, so you start looking at the match since 7:30, so you can see the first ball, and that's what neutrinos allow you to do. This is called early warning system. Actually, there is something called as a supernova early warning network, where if neutrinos come from some object in the sky, then an SMS can come to your phone. So I will get an SMS, for example, if suddenly a lot of neutrinos are coming from the sky. SMS will go to many of the observatories which have optical telescopes or X-ray telescopes or gamma ray telescopes, and all of them will now turn in that direction so that they can see a supernova happening from tomorrow onwards. So neutrinos actually help us in making you aware that something is going to happen in that part of the sky sometime very soon. So that is quite important. Second thing is this plot that you see, which was Indumati kindly showed it in front of us. See, this says x-axis is cosine theta. So cosine theta equal to 1 means that you're pointing to the center of the sun. Okay. Now, if you plot the neutrinos that you observe in a detector like Super Kamiokande, which is what you see on the right hand side, you will see that there is of course a big background for which you can say nothing. But a lot of neutrinos are actually coming from the region between cosine theta 1 and 0.8, which means they are coming almost from the sun. Okay. So yeah, so from this you could actually see the sun. I don't know if Indumati, you have the actual photo of the sun from neutrinos. I have it. I can.
No, I don't have it, so you can share it then.
Maybe sometime later.
Yeah, because I have it, but this is the one I found fast. So there are so many talks. No, I have to just find that.
Maybe next questions can start.
Yeah.
Okay.
Fine. Yeah. So I think that answered that question. So there's a question on I think that particular question was answered, how to distinguish them. Is it possible to do theoretical research projects, internships at PtRC and ICHEP besides experimental ones, especially theoretical summer research projects? So Vivek, would you like to answer this?
I thought you should answer that.
Okay, I will answer this. I'm okay. I guess if everybody doesn't know, I am a theorist. I'm not an experimentalist. Right now, there is one aspect of work at PtRC or ICHEP where you can actually do a simulations project, where you can actually simulate the detector and simulate the kind of events you're seeing there and do physics simulations of what you expect to see at the detector and see if it is consistent with what actually is being seen at the detector. So that is the only kind of theoretical research project or internship that you can do, which is a simulations one. If you actually want to read theoretical physics, it cannot be at PtRC or ICHEP. But I think I said this yesterday also to the same group that you can try with various research institutions across India. Because of COVID, many people will not be able to offer you accommodation, which is what is required for a summer project student. But on the other hand, if you're staying in that city or town, you will be able to actually communicate with them and see if you can, meet them once a week or something like that while staying at home. Okay, so please do try such things. As I said, this year, it's kind of all open. You don't know what will happen as much as you. So you can try. But if you want to do anything at all with PtRC and ICHEP alone, it can only be simulations. Okay,
I just found the photos. I just shared.
Great. Please share it. Please share it. Yeah. Lovely.
See this? It's very, very pixelated, but that's because the direction of neutrinos are not very well known. But what you see here is actually the sun. Okay, and this is no light. This is only neutrinos, and this is plotting number of. So the white region means that number of neutrinos is very, very large, and blue means that it is very, very small. Blue or black means it's almost zero. So this is the sun as seen in neutrinos. Because the direction is not known very well, the size of this photo is quite large. It's almost 20 degrees or so, this circle that you can perhaps see here. Also, the exposure time of this photo is 15 years. Okay? It's like having the camera open for 15 years and seeing what is there. And that's what Super Common Fund did. Okay? So I just wanted to share this.
Yeah, but the amazing thing is that you can see the sun in neutrinos.
other than in light.
Yeah, other than in light. Yeah, you can actually reconstruct the sun, and it looks pretty much like the sun.
Something also important, by the way. When you look at the sun, you look at the surface of the sun. Okay? You can never see inside the core of the sun. Okay, when you take a picture with light, right? Now, what you are seeing here is neutrinos that are coming from really the core of the sun, not just surface. So you are actually observing inside of the sun and not just outside of the sun. So that's quite crucial.
So Shekat Saha has a question. Can engineering physics BTech students take internships with INO and sorry, BRC? Sorry. Vivek, maybe you can answer.
Hello? Yes, interns from the engineering disciplines are certainly welcome if you're interested in the kinds of things that we are doing. And I'm sure you will find it very invigorating to work with your hands at Madurai, at the Transit Campus Lab at Madurai.
So again, one thing I might add is sorry, Satya, you're saying something?
Yeah, you go ahead, Amal.
No, I was just saying that what engineering physics students learn, I was an engineering student, physics student once, so I know, it is actually quite useful for INO. A lot of INO is actually electronic. Okay, and I understand that electronics forms a very large part of education of engineering physics students. So they have the basic knowledge of physics and they have the knowledge of electronics to go with it. Satya will perhaps tell you better about how many students who came with the knowledge of electronics have actually done quite great work in our INO. I leave it to Satya. Satya, go ahead.
Thanks, Amal. That is anyway hearing from the lion's mouth in some way. But just to add, I think this question was also asked in the morning. So I just repeat that there were, out of about 50 odd students who have joined our graduate studies. You in fact heard from one of them this morning, who gave you a talk on the spin-offs, right, of INO project. And he himself is an engineer, and there are quite several of them, and who did fantastic work, and their work directly helped the design of the iCal detector, as you have been seeing today and yesterday. And of course, I mean, there are the capabilities or the knowledge in domain knowledge that you call differs from MSc, a science trained student from technology trained student and so on. But as I, even though let me kind of repeat what I said in the morning, that INO requires real capabilities of heterogeneous, capabilities and talents. And the project is such a big one. It encompasses the science, engineering, mathematics, software, and, even in technology, every conceivable field that you can think of what is taught, there is going to be deployed. It could be detectors, it could be electronics, gas systems that speakers talked about just now, the software technology, the electronics, the so-called ASIC chip development, application specific integrated circuits development, and a lot of data acquisition system paradigms and so on. So often we say, if you actually look at the syllabi of the training school, the PhD school of INO, you'll find that there are only two subjects, if I can call them, as a theoretical subject. One is particle physics and other one is neutrino physics. Rest of the 6 subjects are actually in some way or the other or engineering flavored subjects. Okay, so that really shows that INO is largely an experimental science project, and also building so gigantic detectors is engineering in some way, right? So you're most welcome. And when you apply to INO school, one doesn't distinguish between whether or not you train in science or technology or engineering. So I think INO is that way a nice opportunity. And of course, nowadays, all the modern high energy nuclear astroparticle physics experiments are of that type. I mean, I don't have to tell you, about LIGO, about ITER, about TMT, SKA, CERN, FAIR. All these experiments are very, very much engineering intensive experiments. And BRC, for example, Baba Atomic Research Center, which is in some sense India's best technology institute, is a big part. They play a big part in the INO experiment. So you are most welcome to come as a summer students to INO campus, and also at later stage maybe you'll be able to even apply for a graduate school. As I told in the morning, we had to discontinue for a couple of years the graduate school. Indu, your mic is muted.
Oh, I'm sorry. I said I hope everybody knows that Dr. Satyanarayana is an engineer himself by training. I have already answered Gokula Prasad. I will move on to Sundardhara's question.
Yeah.
Being a PhD, yeah.
Indu, I'm sorry to interrupt you. I'll be back in 5 minutes.
Sure. Being a PhD research scholar student, how can we join collaboration research work with INO or any of you professors? Amol?
Yeah, well, if you are already doing PhD in some universities, then of course the way to work with INO is if your advisor, for example, can collaborate with INO. So as you said, INO is always happy to collaborate with people from all universities who are interested in working with this. So if you have a PhD guide who's interested in collaborating with INO, of course they are very much welcome. So you could try to implore them to do that. And of course, if you haven't chosen a guide yet, then you could try to choose a guide who has interest in these topics.
Yeah, I think that was clear-cut enough. Krishna says, I'm a final year BSc physics student affiliated to Pune University. What is your advice for young and aspiring researchers? What points should a student consider while choosing their mentor for a thesis research project? What the mentor expects from the student when they are selecting them? So it's a very precise question. Vivek, you would like to answer this?
Well, let me see. The first question is, what is your advice for a young and aspiring researcher?
He's a final year BSc student.
Yeah, I know. So I think you should keep your ears and eyes open for things that interest you. Ultimately, the problem that you take up or the area that you take up should be of your interest. I mean, you should not be saying that, oh, why did I get into this? So this is one criterion I think that you should look into and that you should decide. What points should a student consider while choosing their mentor for the, but again, before completing that point number one, be open to possibilities. Okay. Sometimes one is biased, probably even unnecessarily so, against a particular area. And so be open to all possibilities, but then choose something which you like. Okay. What points should one considering their mentor? Okay. Of course, if you have a very good mentor in your university, that's great. If not, then probably look for another place where you have you can nowadays communication is fantastic. You can write emails and you can also look at what possible mentors are doing. And if that interests you, then you can communicate to them and then probably get into that institution. Of course, this would require time because there are fixed periods normally where you have to give your interviews and this and that. But so that provides some constraint, but given time, you can choose your mentor. What does the mentor expect from a student when they are selecting them for working on a thesis research project? I mean, usually the mentor, the student is sort of fresh. So the student would not know a lot of things, but he should be willing to learn. And that is probably what the mentor expects. And also the ability to work hard and think on your own. And if you still cannot solve, then talk to your colleagues, to your mentor. So that is my advice. Maybe Amol can give his advice because he's probably mentoring students right now.
Well, I can tell a story. I can tell Akbar Birbal story.
Okay.
So Akbar, this is again no offense to anybody. So Akbar Birbal was of course the chief minister of Akbar, no? And however, once some people told Akbar that you are favoring this guy Birbal too much. No, I have this guy. We have, in fact, the story is that one of the Begums of Akbar told him that, no, my brother is more intelligent than Birbal. So why don't you make him the chief minister or the wazir? And so Akbar had to make him the wazir. And that's it. So things started. Once, while standing outside in his on top of a hill, Akbar was looking around at his kingdom, and he saw that far away in the desert, a caravan of camels was going. So the wazir was, of course, next to him. So he told him, why don't you go and find out what's happening there? So this guy was young, enthusiastic, ran to the caravan, then came back sort of a bit huffing and puffing and told, this is a caravan of camels, which is going towards, I don't know, let's say Jodhpur. Akbar said, but what do they have? Okay. So this guy went back and again ran there. Half an hour, came back, immediately gave this guy the answer, saying, no, they're actually carrying wheat. So Akbar said, is the wheat any good? He said, okay, I'll tell you immediately. He went, ran there, said, come back after half an hour, again huffing and puffing, said, no, it's very, very good wheat, very good wheat. No, I don't know, so Akbar said, no, what about, is it, can we buy, will the seller this wheat, can you buy this wheat? So this guy went. But this guy was so tired, 3 times he went, he came back. Okay. And by that time, Mr. Birbal was sort of walking very slowly, came back and told Akbar, this is this is a wheat going to Jodhpur, but it actually came from this wheat fields of Punjab, where you actually grow very good wheat. The rates are small, they're going somewhere else. But I told them that emperor wants to buy the wheat, they're willing to sell at a low price. I already told our treasurer to pay them, and I told them to turn this caravan towards Agra, okay, where the capital was. So what your mentor expects you to do, it's something more than what the mentor tells you to do. Okay, see, right now you are perhaps doing your BSc or MSc, where what you do is limited to what question is asked. You are asked a question and you answer the question. That is your job. When research starts, something more is expected from you. You should try to see where your mentor wants to go. What is your future path? And you should take steps such that you are perhaps a few steps ahead of your mentor. You should have thought something more, and perhaps when you go back to meet him or her, you should have done something more than what you have been asked to do. Okay, so my advice is this is what mentor expects from his chief minister, which is going to be you as the PhD student. Yeah, this is my favorite story, which I tell everybody when I get a chance. Go ahead.
Yeah, so I think that the person who asked Krishna Snehal Kumar, got much more than the answer to his question. So Amol has been a very good student. So I cannot resist adding one more point to this. I think that the main thing for young researchers, young students, is to find out what they know and what they don't know. I think this is something that many students don't know. I certainly didn't know when I was young. You have to know what is it that is clear in your mind and where it is that you don't understand, and only then you can actually learn those new things. So when your advisor asks you, do you know this? You shouldn't say, oh, maybe I do, maybe I don't. You shouldn't get, panicked about, maybe I should know this and I don't know this. I think the first thing to find out is, you go over, it's not just answering questions in an exam, but it is to ask, suppose I want to teach this subject to somebody. How well do I know it? Do I know it well enough to teach it to somebody who doesn't know the subject? And I think you should start from there. I think once you start asking these questions, you automatically become a researcher. So that is my, I could not resist adding my piece of advice. So I'll move on to Kiran's question on, can we do project or research without entrance exam like NET-GATE, or is it compulsory? I am actually not sure of the answer to this, because institutions like IMSc only take students through JEST and NET-GATE. I am not sure about whether it is possible at all. I leave it open to anyone who wants to answer this. Vivek, Amol, Satya.
So I guess so this is my information. So of course, if you want to do a PhD in the institution, you have to get through the entrance exam that the relevant institution gives. That could be NET, that could be GATE, that could be JEST, or that could be like a TIFRI's own entrance exam, for example. Okay? If you want to work as a project assistant, I think that if you have cleared entrance exam like NET or GATE, that allows you to get a certain level of stipend. If you just want to do a project and have no expectation of any stipend, then of course it's possible to do, but then that's perhaps not good for you, because it's always good to be at a place where you also get some remuneration for helping in doing research. So there are different levels of doing research. Indu, you are
yeah, sorry. Maybe I should add one point, that some research institutions take people after their BSc. So certainly our institute does, many other institutes do. So those of you who are impatient and don't want to wait until you finish your masters, maybe you can even think of applying after your final BSc. Okay. About the actual marks and ranks, that depends on institute to institute. There is no common cutoff. For example, whatever the GATE exam, no, because it's a percentile, right? So there is a certain cutoff number that can change year by year. You have to look at each year the conditions for admissions. For example, even in JEST, although the rank is given to many more, few hundred people, I think IMSc only calls the first 70 or something. So every institution you will have to, unfortunately this is true, for every institution you have to go and check out in the admissions what the qualification ranks are. Okay. So as I said yesterday, that just last week we completed our selection process for this year, but you can look again next year. So I think that the short answer to Kiran's question is that most likely you will have to have some kind of an all India national exam rank in order to join a research program somewhere in India. Gokula Prasad asks, I completed my MSc Physics this year, preparing for GATE. I want to do PhD in high energy physics. What GATE score or rank should I aim? I don't know. It is the top few percent, I think, so again, it's a percentile. It again will vary from place to place, but certainly you have to be in the top few percentile, I think, in order to enter high energy physics. So that is coming to Anupam Sharma. In experiments related to indirect search for dark matter with neutrinos, scientists are looking for an excess of neutrino events in the direction of the sun. This is dark matter, possibly formed via the decay of annihilation products of dark matter particles. My question is, if such a neutrino is detected in the direction of the sun, will its energy be higher or lower than the energy of a conventional solar neutrino? That's a very nice question from Anupam. Amol, do you want to answer this?
So the answer will actually depend on what is the mass of dark matter.
Amol, you cannot be heard. I think somebody needs to mute.
Yeah. Amol, can you, I think your volume is not enough.
No, now it's clear. No, there was some disturbance.
Okay.
So
yeah, proceed.
The answer to this is that it will depend on what is the mass of the dark matter particles. So normally what happens is dark matter particles annihilate, they come together. So let's say mass of one particle is m. Okay? When they annihilate, the total mass, which is 2 times m, gets converted into 2 particles, 2 neutrinos, whose energy is n. Okay? The energy of neutrinos that come to us essentially will depend on the mass of the original dark matter particle. Now, if the mass is very, very small, of course, these are going to be hard to detect in the INO detector, because INO will only detect those particles if the energy is above a G or so. So clearly, it will be more than that of conventional solar neutrino. I don't know if it was mentioned in the earlier talks to you, but indeed, INO can detect such neutrinos from the sun, which can come from annihilation of dark matter particle. And I think 1 or 2 INO graduate school students have done their thesis on this. So this is also something that you can explore at INO.
So basically, since we don't know anything about dark matter, we don't even know whether they are particles, by the way, and we have no idea about the mass. The mass range that is currently allowed is huge. It will depend on the mass range. As I said earlier, the mass is related to the energy because E is mc squared. And what ICAL detector is sensitive to are kind of GeV energy or GeV mass neutrinos or particles. Okay, so that is the answer. Gokula Prasad asks, can we expect to see Betelgeuse explode into a supernova in our lifetime? Well, I wish. I mean, let's see.
Depends on what is your lifetime and what is Betelgeuse's lifetime.
Yeah. So these are all statistical, right? No one can tell you exactly to the day until actually it is seen. The rough number is about once in 30 years to actually see one in our own or nearby galaxy. But 30 years has passed since 1987A exploded in the Large Magellanic Cloud. But as I said, these are all statistical expectations, so we actually don't know. I'll be very happy to see it explode. I mean, absolutely thrilled, I can tell you, because you will see a huge number of neutrinos from that star. It's so close to us. Okay? Gopal Garg, do non-relativistic neutrinos oscillate? If yes, can you tell us more about oscillation phenomenon of non-relativistic neutrinos? Amol?
So non-relativistic neutrinos essentially would mean neutrinos which have very, very low energy. Okay? So mass of the neutrino is less than electron volt. Okay? And therefore, non-relativistic neutrinos will have kinetic energy which is much less than 1 electron volt. In principle, they can oscillate. Okay. However, the kind of pattern that you see perhaps would not be the nice pattern that expression that you might have seen, which look like delta m square L by E. Okay, the form in which the masses and energies enter in the expression will actually change. There have been papers on it. I do not know a reference offhand, but if you write at some point of time, we can send you one reference about this. Or just look on the Google for oscillations of non-relativistic neutrinos. You perhaps will find something. These are going to be extremely hard to detect. Remember, because these neutrinos will have energies even less than a few tens of electron volts. Okay, So even if they did oscillate, it would be quite hard for us to see that.
There is also something called coherence. You've learned the Young's double slit experiment. So you know that you must have a single light source in order to see interference patterns. It's like that. So there's a certain coherence requirement that is very, very hard to maintain with non-relativistic neutrinos. So there's also a difficulty there. Raghav Krishna asks, can we do dark matter summer research projects? Well, I guess I'll answer this myself. Yes, surely you can do. Not necessarily with INO, but yes, you can try. You can try with some of the theorists who are working on the INO's physics, but there are many high energy groups across India where which work on dark matter. Surely you can look up. All the institute websites will have details of the kind of research that they are doing. You can look this up and certainly you can do this. So Krishna asks, what should a physics student learn before diving deeper into neutrino physics and doing an internship with INO? What set of skills should I have? Vivek, would you like to answer this?
Yeah. I hope you like experimental physics, because the INO project is an experimental project. And so if you like dabbling in electronics, if you like dabbling in making detectors work, or maybe analyzing the data that comes out of these detectors, then I think you will like doing what is being done right now. So right now at the ICHEP, there is a cosmic muon veto detector that is getting assembled. And in the near future, of course, it might take about a year and a half or so, the RPCs will be put into the engineering ICAL model. Of course, before that, we also are planning to refurbish the 2 meter by 2 meter RPCs, of which we have something like 250 or something, 250, 300 of them. And we have made a special arrangement for that. So to clean up the surfaces which didn't have very good coatings. So we are going to recoat them, and we have a special chamber to do that. And so this is another experimental aspect that if you get hands-on experience, this will be useful, very useful. Perhaps even when these things are applied for purposes of monitoring containers and things like that. In fact, many of the high energy physics PhDs have branched out into applications abroad. They have even, for instance, started companies of their own. Experimental physics is what you would be working on in the project such as this. But if you don't like experimental physics and if you like only theory, then of course there are also possibilities. There are many phenomenologists, as I said, and you can write to them what is it that you like to work on and so on. But we would of course prefer that you work on experimental aspects, because this project is mainly an experimental project.
So basically, if you like to take apart your toys and put them back together again, that's a great skill set to have. Okay? And I mean it seriously. Okay, I think that labs in India are really in a pitiful state. There are very few labs in universities or colleges in India which actually do a decent job of training you. That's really unfortunate. So if you just like to fiddle around with your hands and meddle with things, that's a great set of skills. Okay, so Ashwita asks, what degree do we have to take after a BSc Physics to become a researcher? Becoming a researcher is a long process. As I said, a PhD is one requirement. Used not to be the case, but it is a requirement to have a doctoral degree in physics. In some institutions, such as my own institute, Institute of Mathematical Sciences, you can directly do a PhD after BSc. In some places, you have to have a master's degree before you can do a PhD. And even after PhD, which can take 3 to 5 years in many cases, you need to get experience by doing what is called a postdoctoral fellowship. So it's called something which comes after your doctorate. It's a postdoctorate position where you don't have a mentor anymore, but you try to strike out on your own, and you try to find your own solutions to your own problems. And it's like being a little bit of an apprenticeship before you actually become a researcher. So it's a long path. I think it's only for those who are really keen on the subject, but it has its own rewards. Ashish asks how to go for thesis work in masters. Amol?
Yeah, well, in some sense, nothing different than thesis work in for PhD. The idea is, the thing is that it's of course a short-term thing. So scope of the thesis work you did masters will be limited. What is important is that you have a good mentor or a guide who will tell you, who will set you on path for a focused research project. So something which will have results in a year also. Okay. So yeah, so there is it's focus so that you can finish something in 1 year. Kind of clear idea of what is going to involve is what is needed. The rest basically depends on your guide. I think it's very important that for doing a good thesis, either in PhD or in masters, what you need is a good guide and mentor. Okay, so even more than the reputation of the institution, what actually matters is a guide or a mentor who sets you on the right path, whose topics you are interested in, and with whom you can get along with.
Okay, so I think it's a similar question. What is the eligibility criteria or selection procedure for applying to any positions, including internship, fellowship, research, or graduate training program by Devanshu Jha? I think Amol, you can just clarify this as well.
See, let's go in a few levels. So one is a graduate school. Okay, graduate school is like for doing PhD, and many institutions will take you for this through their entrance exams. Okay. Now, one of the major entrance exams which is accepted by institutions in India is called as JEST. Okay, it's a joint entrance
screening test. Yeah.
This is a test in physics. And I think if you clear this, you will be called by almost 25 big institutions in India for admissions there, okay? For interview at least. In addition to that, there are many universities in which you can also do PhD by going through proper channels, maybe by going through NET exam, for example. This is also true for any graduate training program. And then, as I mentioned to you earlier, if you don't want to do a PhD, you simply want to become a research assistant, then of course there are positions available, but each of the positions will have their own criteria depending on what is the institution and so on and so forth. For internship, which is normally something that you do in your summer break or something, the idea is to write to people, showing them your interest and asking them what you can do. Internships typically do not get paid. You are essentially working for getting experience during your summer breaks, and those are possible to obtain. However, remember that it is not that you write to one person that you like a lot and you will get internship with them, because sometimes people are in demand. So do write to a lot of people in whose work you are really interested, and once you do a good internship, then the word spreads, okay, and then you can get nicer opportunities afterwards. Yeah.
Amol, I think many places internship they are paid, no? Summer programs.
Sometimes they are.
Yeah, sometimes they are. Yeah, it depends. I mean, if a summer research, summer student program is advertised, normally they pay something like 200, 250 a day or something like that. Okay, yeah, so and then they give you free accommodation, stuff like that. So, yeah, so that's also there. Yeah.
So for summer internships, yeah, institutions do have what are typically called as VSRP programs, or visiting student research programs, for which if you get selected, then you can also get paid internship during that. Yeah.
Also, the Indian academies also have their own.
Yeah. Yeah, I think that's a very important thing.
Yeah. About 400 students every year are taken. About 100 faculties and about 400 students are taken every year. And actually, they have a better, like what Professor Amol Dighe said, they have a little better reach, I would say, because they do ask to give choice of faculties and the institutions. And usually they get a more percentage of satisfaction of getting the first choice and so on. And this is also, it works exactly like what he said in terms of VSRP of TIFR or IMSc or other institutions.
So this is actually all the 3 academies of India, science academies of India, getting together to host this program. So it's a very nice one. I think we should look that up also. So that is one thing. The other thing I wanted to say was about
Okay. I'm muted. Yeah.
Gokula Krishna should mute his mic, I think.
Yeah.
No, I am muted.
Yeah.
Oh.
So I think Raghav Krishna has a similar question to his earlier one, summer research project in dark matter. It's the same thing, whether you want to do research, summer research, project, whatever it is. Please look at various, actually go to INO webpage. Go and look at the list of institutions which are participating. All of them have a high energy physics group. Go through their lists, find out the person who's working in dark matter and write to them. And as I think what Amol said was very, very correct, please don't write to 1 or 2 people because typically we have hundreds and hundreds of people who apply for summer positions every year. And for example, IMSc only takes 12. But if you are in Chennai, then we have no limit on the number. You can come anytime. You can talk to any one of us. We are a very open institution. And we'll be very happy to host any of you. And there are many such institutions. So just do your research, a little bit of research on who's doing research in the area that you like. Write to them and try to find out about them. Find out all possibilities. There are some people whom I'm mentoring online without even they are coming to Chennai. So everything is possible. Just write to people and find out about it. And that's the way to go, I think. Okay. Yeah, after BSc degree, you can take any research field. Yes, sure. That's what Satya asks. Yes, you can take any research field that you like. That's your choice, in fact. What is the current salary for researchers at INO? I think Satya is the right person to answer this. What is the current number? Satya,
sorry. I mean, researchers, is one talking about?
No, he's talking about PhD students, I think, right?
PhD students, they get around 40, no, about 70, I think.
30 something.
And 30 is their, this one. There is also, what do you call? Book grants and so on. I think that is around 40. Sorry, the other one is equal number, around 40K.
No. Stipend is around
Stipend is also around 40K. 30 or 40K.
No, 30,000. Okay.
30K. Okay. And free accommodation and also the transport and so on.
Yeah. But this is of course if you're a graduate student. I mean, if you
graduate students, yeah, PhD student.
PhD student, yeah. If you're not a PhD student, then it's slightly less, I guess, if you only come after this.
Yeah, but roughly this is the order of magnitude. Okay?
This is order, yeah.
Order of magnitude, yeah. Okay, fine.
Correct.
So the 30,000 is what I've written, 40,000 per year book grant. Then you will get some money for buying a laptop and various things, all kinds of things are there. So these are round numbers.
And also, there is some stipend or some help given for the students to attend
conferences. Yeah, correct.
They present their papers. That is also there.
Yeah, correct. Okay, so Gopal Garg asked, I've just completed my master's with specialization in high energy physics. Due to the lockdown time, most of our class was conducted online. I don't have good knowledge in computer programming. Can you tell us about essential knowledge in computational programming, especially in the field of high energy physics, especially in neutrinos? So, what have you learned, Gopal? I mean, have you learned some basic C, C++, Python, Java, anything, programming?
Yes, ma'am. I have learned C+ and Fortran basically.
Okay, I mean that is very good. So what you need to do is, I think, apart from computational programming, you need to know some certain methods, numerical methods in physics that are constantly used. For example, in linear interpolation, then solution of differential equations. What else? Then matrix inversions. Then there will be best fits. Linear best fit, non-linear best fit, chi-squared. So these are the kinds of things that we use very commonly in the kind of computational program we do. So if you have a good knowledge of this, that should be just fine. So Pushkraj says, we are doing outreach programs for locals and also others in English and Tamil. Would there be any chance of such programs in other states and languages to reach more people besides the scientific community? It's a lovely question. Maybe Amol should answer this.
Yeah, well, so of course, talking about neutrinos or science in different languages depends on the people from those languages who are willing to conduct such programs. So my suggestion is that if you do want to conduct such a program in some language, first try to contact people who are, let's say, native speakers of that language who would be willing to teach in these programs. and we can see maybe we INO can help you organize such a program in that particular language. So I think we are always willing to. I mean, of course, this was in Tamil, but no, I can speak in Marathi. I'm sure Hindu can perhaps also speak in Telugu, and there are people who can speak in Bengali. So it is possible to conduct this, but yeah, somebody can take the lead and we can help.
Yeah, so I think it's a very nice suggestion. I think if any of you is interested, if you think that there is an audience who is interested, please write to us. We will try to find the person in that appropriate language. Many languages, in fact, are spoken by many of us, and we will try to organize such a meeting. Surely we can do it. Okay. We opted for Tamil and English because the project is coming up in Tamil Nadu, and English is something that most of us speak. But we will be very happy to have this program in other languages as well. Okay. Please, Pushkraj, if you know of such interest, please do get back to us. Okay. Shaikat asks, can an engineering physics student join the recently introduced DRDO courses for MTech? Are they worth it for students with interest in R&D domain? This is the Amrita course you're talking about, is it? I know of one Amrita course which is jointly done by the MTech group. By the Amrita group in collaboration with DRDO. Is that the one you're talking about?
Ma'am, this was introduced by DRDO and AICTE recently.
Oh, the AICTE program. Oh, okay. Yes, that is very recent. I would not know. I mean, they just announced it a couple of months back, right?
Yes, ma'am.
So I don't know really. I mean, I have no idea. Is there anyone who knows anything about it?
No, I have no idea.
Yeah. Actually, can you hear me?
Yeah. Go ahead, Satya.
Yeah. So, I mean, such programs existed earlier with other government relations. For example, Space had such programs. DRDO particularly used to have programs earlier in Pune with their institutes and so on and so forth. But now what they're doing is they're actually making a regular MTech program, but specializing only in the technologies that are relevant to them. And also, but this time they brought AI itself in the picture, but slowly the AIC slowly with us for the this one. But nevertheless, these courses are somewhat specialized. And they will only would have which are going to offer these courses. They get limited, but there are kind of MOUs that are signed by specific engineering colleges and with DRDO. DRDO also offers teaching faculties and also their laboratory and other facilities, whereas the regular other courses are actually taught by the local faculty. So recently, the DRDO chief, Dr. Satish Reddy, has announced this, and the inauguration was done in July sometime. So it's a good course, unless you kind of decided that this is the line that you are going to go on. And DRDO, of course, is home to many such organizations, many technologies, and that, right? Just like CSIR, DRDO is one institute where they work on varieties of things. So if your interest is in that, I think it's a good course. It's very good, but except that, then you are already focusing your energies into a particular field, namely defense technology.
Yeah, but I agree with Satya that DRDO has a lot of state-of-the-art equipment. Their labs are, absolutely fabulously funded and fabulously equipped. So if you're interested in that kind of thing, I think, it will be a very good thing. And I'm sure that because they have this tie-up, they will also probably give you certain preference in actually joining the defense group afterwards. Because DRDO also absorbs a huge number of, by the way, chemists, physicists, and they usually look at both MSc and MTech for their hiring. Okay, so maybe you can. I don't know. Beyond that, I don't know. Thanks, Satya, for clarification.
This program is good, unlike the earlier programs which were directly from DRDO, but now
I see. Okay,
tied up with engineering body.
Okay, that is a very good thing. If it's tied up with the AICTE, even I didn't know about it. Yeah, I just found out.
Yeah, this is Satish Reddy's initiative.
Oh, nice, very nice. Then of course Satya's word is to be taken seriously. Okay. Okay, we are back to physics. Nice. Raghav Krishna says, do neutrinos undergo diffusive shock acceleration at supernova shock wave fronts, as there will be magnetic inhomogeneities at these wave fronts? Now, I think that whoever wants to answer this question must please explain the question to the rest of the audience, because it's a very technical question, and then give your answer. So I don't know, Amol, you or I think one of us can answer. You can answer.
Yeah, I can go ahead, and whatever I'm missing, maybe you can.
Sure.
So this question is about the supernova explosion. Okay, now the explosion, when the explosion happens, what's happening is that the shock wave which has been produced keeps on moving outwards till it tries to blow up the star. But at the same time, neutrinos keep on being produced in the core of the star, and they keep on coming out through the shock wave. Okay? And the question is there a diffusive shock acceleration of neutrinos at the shock wave fronts? Now this comes because if you have heard, there is something standard thing called as a Fermi shock acceleration mechanism, which happens when charged particles pass through shock fronts. Now, neutrinos in a supernova will not undergo this kind of acceleration for two reasons. One reason is that they are neutral particles, because they are not charged particles. And you know that in order to get influenced by magnetic field, the particle needs to have a charge or a magnetic moment. Okay, neutrinos have zero charge and a very, very tiny magnetic moment, so they will not get affected by the shock waves. Second reason for this is the neutrinos are extremely weakly interacting, and actually what happens is that these neutrinos pass through the shock fronts without getting affected. Okay, so usually the densities that take place at these shock fronts are of the order of maybe 1 lakh to 10 to 100 lakh grams per centimeter cube. The density looks quite high to us. However, it is quite possible for neutrinos to pass through such densities without interacting. Okay? So the neutrinos simply don't interact in this, and therefore do not get affected by magnetic fields or shock fronts that happen. Okay? Neutrinos have other effects of the shock front, yes, but that has to do with their oscillations and not about shock acceleration mechanism. Maybe Indu wants to add something more?
No, perfect. There is nothing more than that, except I think that we go on again and again saying that neutrinos don't interact much. Okay, I think this is the I don't know, the highlight or the obituary, I don't know which of INO, that whatever people may say about neutrinos causing damage, ultimately even such neutrinos, they go through even such high dense matter as those in shock wave fronts in supernovae. I hope you know that the core of the supernova is at nuclear densities, and leaving behind very often a neutron star or black hole. And even then, these neutrinos free stream through practically, right? So that's it. So I can't see any other question. Okay, Anukalpa says she's very happy to have participated in this, and she wants to take up masters in astronomy. So what are my options? Astronomy, I guess. Somebody else was in Pune, right? I mean, both IUCAA and NCRA are in Pune. There is Raman Research Institute and Indian Institute of Astrophysics in Bangalore. So let me just start writing. Okay, so these are institutes which are, as you can see, the A standing for astronomy or astrophysics in IUCAA, NCRA, and IIAP. So there's a lot of astronomy going on there. I am sure this. What are the other places?
I think PRL is also another institute where they use infrared astronomy and so on.
Yeah, PRL has a lot of infrared astronomy. Correct.
So most of these institutions have a program in astronomy for PhD. Okay? I'm not sure if they have a program specifically for masters in astronomy. However, you can do masters, and while doing the masters program, you can do a project with one of the astronomers of the institution. Okay, so the degree will still be a BSc in physics. However, you will get to do your project in astronomy.
Okay, good. Any more comments? Okay. Fine. Yeah, oh Krishna, I would love to interact with you. I will send you my email address. Ashish says, tell us a bit on how to go for write-up or SOP. What points should we mention regarding our topic and what are the expectations? I think Amol has his nice stories for all occasions. Amol?
I didn't have a story for this, but I just want to tell you that from SOP, the expectation is that you write what you feel very honestly. Okay? What is required is that when we read a SOP, you should give a very clear picture of what your background is and honestly say what you know and what you're interested in. It is not what people are looking for is not what great things you have or that you're interested in everything or that you know everything. Depending on, see, the reason the SOP is there is to tell the people what is it that you know. Because based on what you know, there'll be something nice that you can do. You don't have to know everything in order to do research. Okay? But depending on what you feel passionate about, a good mentor will be able to suggest a good research project in which you can prosper. So therefore, it's very important to be very honest and say, I like doing these things, I do not like doing these things, and this is what I have done for them. I think because very, very important thing that I have found in these years is that you succeed well in research if you really, really like what you're doing, and not because you want to do something very fancy or something which is really the top thing. So we just we recommend honesty.
Okay. I think now it is almost for 4:30.
Okay, we will take maybe last 3 questions if there are. So Pushkraj to Vivek. Vivek, can you please explain, Vivek sir, explain the experimental part of INO. What's the theoretical part from, sorry, I lost that. Just a moment, please.
What is this?
What's the theoretical part from research perspective for physics students?
For a physics student. Well, I think he's asking for what theory can be done. So I think
but you actually heard a lot of it, right? You heard about atmospheric physics, dark matter physics, all of that kind of thing is the theoretical part, right? You have a favorite model for dark matter. You can see what its signature will be in, say, the ICAL detector. You can look at that, or you can write your own model, and then you can leave it to others to find out what will be the experimental signatures in the detector. You can look at what happens if you don't have just the standard model of particle physics, but you have some physics which violates what is already known, maybe some physics beyond the standard model that we understand so far, and how you can actually look for evidence for such things. I mean, these are all the things that you speculate, and then if the experiment actually finds it, then of course that theory is in better shape and on more solid ground, and then you continue in that direction. So there are 2 kinds of theoretical physics. One is just pure theory, where you do model building and don't care too much about what the experimental outcome is. Then there is something called phenomenology. And in phenomenology, actually, you make a bridge between the theory and the experiment, because nowadays the experiments are so complicated that you have seen. The theories are so complicated, maybe you have not seen so much about that, but it becomes very difficult for a pure theorist to actually know what that theory will predict with respect to that particular experiment. So that bridge is built by a phenomenologist who, in the words of the phenomenologist, will understand both the theory and the experiment and will translate the predictions of the theory into specifics that the experimentalist can actually measure. And of course, if he's a good phenomenologist, then he's a great guy because he knows both theory and experiment. And if he's a bad phenomenologist, then he's a bad scientist because he knows neither experiment nor theory well. So it's a very kind of a, it goes around and around, it's like a ringa ringa roses kind of thing. Nowadays, you don't have very clear-cut, partitions of these things into theory and experiment. So there's a lot of overlap. And so you can just find the place where you're comfortable and work in that area. Okay? So that is an answer. I think maybe Satya has given us warning. Let us go. I am from Chennai. Who is from Chennai? Sorry. Oh, Rado. Okay. Thank you. Thanks a lot. Thank you all. What is the grant? Contact us. Yes. Thank you for the SOP guidance. I've saved all your email IDs. Amol sir's email ID is Amol can type it himself. Yeah. Yeah. Thank you so much. Yeah. I do hope. Well, I do hope the INO will begin soon. If it doesn't, it's not because of any lack of enthusiasm on your part. I hope that we will build it and all of you will get an opportunity to work on it. So I think you are all very obedient students because Satya said stop and you all stopped asking questions. So I hand it back to Satya for further comments. Thank you all. And all the best, by the way. It's nice to see on a Sunday and Saturday this kind of enthusiasm from college students. I really, really appreciate it. I wish you all the best and hope that I will see at least some of you soon, sometime in the future. Thank you all. Satya, yours.
Satya perhaps.
Yeah.
I thought he's just come back. Yeah.
Can you hear me?
Yeah. So we can wind up, Satya. We have.
Just a second.
Yeah, sure.
Just give me 1 second.
Sorry. Vasikaran is asking about certificates.
Just give me 1 second.
Okay. Everyone will wait for.
Yeah. Okay.
2 minutes. Okay.
Yeah. So thank you all of you, particularly Amol, Professor Amol DK, Professor Indumati, Professor Vivek Datar. I think this was longest session on this kind of matters in all these campaigns, and also brought up almost every single conceivable question from the participants, not just only about physics, but lots of other things. So thank you so much for patiently answering each and every question. So with that, we conclude this particular session, but also more importantly, the entire outreach program. So this is, I think, a nice time to kind of thank once again on all your behalf, all means the participants' behalf, to thank our faculty who has been from almost last 2.5 to 3 weeks, took so many sessions for you. Professor Rajshekaran, Professor Indumati, Professor Murthy, Dr. Petiraj, Mr. Krishnamurthy, TV Venkateswaran, you heard, Jones Panicker, Professor Datar, Professor Mazumdar, the Project Director of INO, Professor Amol DK, Professor Sanjeev Agarwala, and Professor Shubhabati Goswami. So I think it is on your behalf, it is a great pleasure to thank every one of them. And more importantly, also thank you particularly to very wholeheartedly participating in this program. And I hope at the end of the day, you learned something that you didn't know before you attended. And at the same time, also, I hope you got lots of information, which is, in some way counter the kind of news and propaganda that goes around about INO Project. But more also importantly, that you understood lots of career opportunities that are waiting for you to kind of take up. So thank you so much that being part of such a nice audience, and more importantly than that is very active and interactive audience. Okay. Now I think Indu was mentioning about these certificates. As I mentioned in your letter, everyone who has attended yesterday and today these sessions, you will be getting the e-certificates in a few days' time to your email ID that you have mentioned in the registration page. Okay, and all the talks that have been given today in this series, not today, since last, they're all available in the INO webpage. Along with the PPTs. PPTs will take 1 or 2 days time because some of the faculties have to share their PPTs. They will be along with the videos that will become available. You click on the description, in the description of video, the slides open, right? So you can also see these slides, okay? And regarding this question, that it is nice question that was asked some time back. If you in your region think that there is you think there is enough audience for a particular language in the outreach program, as already our faculties mentioned, please feel free to write to us. We did such programs in the past, so we can do it again. There is no problem at all. In any Indian language, we do have because INO is, of course, a project which is a national-wide project. And we luckily have faculties who can speak almost every Indian language. So feel free to kind of propose things. Okay. I think beyond that, it is all wishing you all the best. I hope the COVID will be thing of the past. And then we will see many of you at the IHF campus in the coming summer and later. And notwithstanding that, all the best for your career. And I hope the whole program was of some use to you in updating your knowledge in this particular field. So thank you once again. Thank you very much.
So I would like to say a few last words, which are thank you so much to Dr. Satyanarayana, who made this entire program possible, the whole technical back end of it, to actually organizing the sessions, to being there for you, answering your questions, and basically, from end to end, everything was done by him. Of course, with his group of people, but he was the prime mover, and I think he did a great job. Thank you so much, Satya. It's been a very long 4 weeks program, and I think that it went off really wonderfully. Thank you so much.
Okay, if it's not too much problem, can we all put on your cameras one for last time, and I'll just click two screenshots.
Yeah, so he's still doing his job, as you can see. Yeah, please put on your video so we can take some screenshots. Quickly.
Yeah, quickly.
Yeah. Please turn on your videos if possible, so that we can see your nice smiles. Come on. Yes, thank you. Some more people, please.
Okay, anyway, nevertheless, let me start. Yeah. Coming. More of them. Excellent. Yeah, come first. Very good. Almost there.
Oh, very good.
Excellent.
Padmavati,
Okay.
I think, is maybe she's not there.
Okay. But you have to give me, I take a little more time. It may not be very quick, so you have to bear with me. Okay. And I have to go to the second. Just one last one. Excellent. I'm done. Thank you once again. So have a safe life these days. That is an important wish that you all have to make. Keep yourself very safe. Take care.
Okay. Yes. Bye everybody. Bye everybody. All the best.
Wish you all the best.